What if you could travel the universe without leaving your bed? Get ready for a cosmic journey that will expand your mind and relax your body. Make yourself comfortable, close your eyes if you'd like, and let these fascinating facts about our universe lull you to sleep. In the vast expanse of our universe, few cosmic entities capture the imagination and challenge our understanding of physics, quite like black holes. These enigmatic objects, born from the gravitational collapse of massive stars, represent the ultimate extreme in nature's arsenal. At their core lies a singularity, a point where the laws of physics as we know them break down, and the fabric of space-time is warped beyond comprehension. The formation of black holes is a cosmic spectacle that begins with the death throes of massive stars. When a star with a mass at least 20 times that of our Sun exhausts its nuclear fuel, it undergoes a catastrophic collapse. The immense gravitational forces at play overcome all other known forces, compressing the star's core to an infinitesimally small point of infinite density, the singularity. Surrounding this point of no return is the event horizon, a boundary beyond which nothing, not even light, can escape the black hole's gravitational clutches. The physics governing black holes pushes the boundaries of our understanding of the universe. General relativity, Einstein's groundbreaking theory, predicts that the extreme curvature of space-time near a black hole leads to fascinating phenomena such as gravitational time dilation. An observer watching a clock fall into a black hole would see it tick ever more slowly as it approaches the event horizon, while to the falling clock, time would appear to progress normally. This mind-bending concept illustrates the profound impact black holes have on the very fabric of reality. One of the most intriguing aspects of black hole physics is Hawking radiation, a theoretical phenomenon proposed by the late physicist Stephen Hawking. According to this theory, black holes are not entirely black, but emit a faint glow of radiation due to quantum effects near the event horizon. Over immense timescales, this radiation causes black holes to slowly evaporate, with smaller black holes dissipating faster than larger ones. A typical stellar mass black hole would take an unimaginable 10^67 years to evaporate completely, far longer than the current age of the universe. The concept of Hawking radiation has profound implications for our understanding of the interplay between quantum mechanics and gravity, two fundamental pillars of modern physics that have yet to be fully reconciled. It suggests that information, which was thought to be lost forever when it falls into a black hole, might actually be preserved in some form, encoded in the radiation emitted over eons. This information paradox remains one of the most perplexing puzzles in theoretical physics, driving research at the forefront of our quest to unify quantum theory and general relativity. As if black holes weren't mysterious enough, some theories propose that they might serve as gateways to other universes or distant parts of our own cosmos. The concept of traversable wormholes, hypothetical tunnels through space-time, has long tantalized physicists and science fiction enthusiasts alike. While classical general relativity allows for the existence of wormholes, keeping them open and stable enough for travel presents significant challenges. Exotic forms of matter with negative energy density might be required, a concept that, while not ruled out by known physics, remains highly speculative. The potential for using black holes or wormholes for time travel adds another layer of intrigue to these cosmic phenomena. The extreme warping of space-time near a black hole could, in theory, allow for closed time-like curves, paths through space-time that return to their starting point in time as well as space. However, such possibilities raise profound questions about causality and the nature of free will, leading some physicists to propose mechanisms that would prevent paradoxes and preserve the consistency of events. While stellar mass black holes capture our imagination, supermassive black holes lurking at the centers of galaxies present an even grander cosmic mystery. With masses millions or billions of times that of our Sun, these behemoths play a crucial role in galactic evolution. The discovery of a direct relationship between the mass of a galaxy's central black hole and the velocity dispersion of stars in its bulge, known as the MS relation, suggests a deep connection between black hole growth and galaxy formation. Observations of the supermassive black hole at the center of our own Milky Way, known as Sagittarius A, have provided some of the most compelling evidence for the existence of these cosmic giants. By tracking the orbits of stars in the galactic center over decades, astronomers have determined that an object with a mass of about 4 million solar masses resides in a region no larger than our solar system. The only known object that can contain such a large mass in such a small volume is a black hole. The detection of gravitational waves has opened a new era in black hole research, allowing us to hear the universe in ways previously unimaginable. The first detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, came from the merger of two black holes, each about 30 times the mass of our Sun. This groundbreaking observation not only confirmed a key prediction of general relativity, but also provided direct evidence for the existence of binary black hole systems. Subsequent detections have revealed a population of black holes with masses that challenge our understanding of stellar evolution. Some of these black holes are significantly more massive than theoretical models predicted, forcing astronomers to reconsider the processes by which stars collapse and black holes form. The possibility of primordial black holes, formed in the early universe before the first stars, has also gained renewed interest as a potential explanation for these observations. As our ability to detect and study black holes improves, we are continually pushing the boundaries of our understanding of these cosmic enigmas. Advanced gravitational wave detectors, both on Earth and in space, promise to reveal the secrets of black hole mergers across cosmic time. Meanwhile, global networks of radio telescopes, such as the Event Horizon Telescope, are capturing increasingly detailed images of the environment around supermassive black holes, allowing us to test general relativity in the strongest gravitational fields in the universe. The study of black holes continues to be a frontier of modern physics, challenging our most fundamental theories and pushing the limits of our observational capabilities. As we peer deeper into the cosmos and refine our understanding of these enigmatic objects, we may find that black holes hold the key to unlocking some of the universe's deepest mysteries. From the nature of space-time to the possibility of other universes, black holes stand as cosmic laboratories where the most extreme physics unfolds. As we contemplate the profound mysteries of black holes, our gaze inevitably turns to the broader cosmic landscape. In this vast arena of space and time, another enigma beckons: the search for worlds beyond our solar system that might harbor the potential for life. The quest for habitable exoplanets represents the next frontier in our exploration of the cosmos, promising to shed light on our place in the universe and the possibility of life beyond Earth. In the vast expanse of the cosmos, one question has captivated human imagination for centuries. Are we alone in the universe? The search for habitable exoplanets, planets orbiting stars other than our Sun, represents a pivotal step in answering this profound query. This quest not only pushes the boundaries of our technological capabilities, but also challenges our understanding of what constitutes a habitable world. The journey to discover exoplanets began in earnest in the early 1990s. The first confirmed detection came in 1992, when astronomers Alex Wolszczan and Dale Frail discovered planets orbiting the pulsar PSR B1257+12. However, it wasn't until 1995 that the first exoplanet orbiting a main sequence star, 51 Pegasi b, was detected by Michel Mayor and Didier Queloz. This discovery opened the floodgates, and in the decades since, our understanding of planetary systems has undergone a revolutionary transformation. The methods used to detect exoplanets have evolved significantly since these early discoveries. The primary techniques employed today include the transit method, radial velocity measurements, direct imaging, and gravitational microlensing. Each of these methods has its strengths and limitations, contributing to our growing catalogue of exoplanets in unique ways. The transit method, which has been particularly successful, involves detecting the minute dimming of a star's light as a planet passes in front of it. This technique not only allows for the detection of planets, but also provides crucial information about their size and orbital period. NASA's Kepler Space Telescope, launched in 2009, used this method to great effect, discovering thousands of exoplanets and revolutionizing our understanding of planetary systems. The success of Kepler led to the development of its successor, the Transiting Exoplanet Survey Satellite, TESS, launched in 2018, which continues to scan the sky for new worlds. Radial velocity measurements, on the other hand, detect the slight wobble of a star caused by the gravitational pull of an orbiting planet. This method has been instrumental in confirming many transit detections and has provided valuable data on planetary masses. The combination of transit and radial velocity data allows scientists to determine a planet's density, providing clues about its composition. As our detection methods have improved, so too has our ability to characterize these distant worlds. The concept of the habitable zone, often colloquially referred to as the Goldilocks zone, has been central to the search for potentially life-bearing planets. This region around a star is defined as the orbital distance where liquid water could exist on a planet's surface, given the right atmospheric conditions. The parameters of the habitable zone vary depending on the star's size and temperature, with smaller, cooler stars having habitable zones closer in than larger, hotter stars. However, the presence of liquid water is just one factor in the complex equation of habitability. Researchers must also consider a planet's size, mass, atmospheric composition, magnetic field strength, and geological activity, among other factors. Earth-sized planets in the habitable zone of their stars are of particular interest, as they are more likely to have similar conditions to those that fostered life on our own planet. One of the most exciting discoveries in recent years has been the TRAPPIST-1 system, announced in 2017. This system, located about 39 light-years from Earth, consists of 7 Earth-sized planets orbiting a small, cool star. 3 of these planets are within the star's habitable zone, making them prime targets for further study. The proximity of the TRAPPIST-1 system and the nature of its host star make it an ideal candidate for atmospheric studies using next-generation telescopes. The James Webb Space Telescope, JWST, launched in December 2021, represents a significant leap forward in our ability to study exoplanet atmospheres. With its unprecedented sensitivity and spectroscopic capabilities, JWST is poised to detect the presence of key atmospheric components such as water vapor, carbon dioxide, and methane on distant worlds. These molecules are not only indicators of potential habitability, but could also serve as biosignatures, chemical signs of life's presence. The search for biosignatures is a complex and nuanced endeavor. While certain molecules like oxygen and methane in combination could indicate biological activity, researchers must be cautious about false positives. Abiotic processes can sometimes mimic the chemical signatures of life, necessitating a holistic approach to exoplanet characterization. Future missions and technologies aim to refine our ability to detect and interpret potential signs of life on distant worlds. As our catalogue of exoplanets grows, so too does our understanding of the diversity of planetary systems in the universe. We've discovered hot Jupiters, massive gas giants orbiting perilously close to their stars, super-Earths, planets larger than Earth but smaller than Neptune, and even rogue planets drifting through interstellar space, unbound to any star. This diversity challenges our theories of planetary formation and evolution, forcing us to reconsider our understanding of how solar systems, including our own, come to be. The implications of discovering habitable or even inhabited worlds beyond our solar system are profound. Such a discovery would fundamentally alter our perspective on life in the universe and our place within it. It would raise new questions about the nature of life, its origins, and its potential forms. The philosophical and societal impacts of such a discovery cannot be overstated. Looking to the future, several ambitious projects are on the horizon. The proposed Large Ultraviolet Optical Infrared Surveyor, LUVOIR, telescope concept, if realized, would have the capability to directly image Earth-like exoplanets and characterize their atmospheres in unprecedented detail. Ground-based observatories like the Extremely Large Telescope, ELT, in Chile, set to begin operations in the mid-2020s, will also play a crucial role in exoplanet research. As we continue to push the boundaries of our technological capabilities, new methods of exoplanet detection and characterization are being developed. Astrometry, which measures the precise positions of stars over time to detect the influence of orbiting planets, holds promise for discovering worlds that might be missed by other methods. Additionally, advancements in coronagraph technology, devices that block out the light of a star to allow direct observation of orbiting planets, may soon allow us to directly image and study Earth-like worlds around nearby stars. The search for habitable exoplanets is more than just a scientific endeavor. It's a journey that speaks to our deepest curiosities about the universe and our place within it. Each new discovery brings us closer to answering age-old questions about the prevalence of life in the cosmos. As we stand on the cusp of potentially revolutionary discoveries, the field of exoplanet research continues to captivate scientists and the public alike, promising to reshape our understanding of the universe and our role within it. As we contemplate the vast possibilities presented by the search for habitable worlds beyond our solar system, we are reminded of the intricate dance of cosmic forces that shape our universe. Among these forces, one stands out as particularly enigmatic and influential: dark matter. This invisible component, whose presence is inferred only through its gravitational effects, forms the very scaffolding upon which the visible structures of our universe are built. As we turn our gaze from distant exoplanets to the fundamental fabric of the cosmos, we find ourselves face to face with one of the most profound mysteries in modern astrophysics: the nature and composition of dark matter. In the vast tapestry of the cosmos, there exists an enigmatic substance that shapes the very structure of our universe, yet remains frustratingly elusive to direct observation. This mysterious entity, known as dark matter, comprises approximately 85% of all matter in the universe and about 27% of its total energy content. Despite its ubiquity, dark matter neither emits nor absorbs light, making it invisible to our most sophisticated telescopes and detectors. Its presence is inferred solely through its gravitational effects on visible matter, leading to one of the most profound mysteries in modern astrophysics. The concept of dark matter emerged in the early 1930s when Swiss astronomer Fritz Zwicky observed the Coma cluster of galaxies. Zwicky found that the visible mass of the galaxies was insufficient to account for their observed velocities. He proposed the existence of dunkel materie, dark matter, to explain this discrepancy. However, it wasn't until the 1970s that the idea gained widespread attention in the scientific community. Vera Rubin and Kent Ford's groundbreaking work on galactic rotation curves provided compelling evidence for the existence of dark matter. They observed that stars at the outer edges of galaxies were moving much faster than predicted by the visible mass distribution. This observation suggested the presence of a vast, invisible halo of matter extending far beyond the visible boundaries of galaxies, providing the additional gravitational force needed to explain the observed stellar velocities. The evidence for dark matter has since accumulated from various astronomical observations. Gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity, allows astronomers to map the distribution of dark matter by observing how its gravitational field bends light from distant galaxies. The Bullet Cluster, a system of colliding galaxy clusters observed in 2006, provided particularly striking evidence for dark matter. In this cosmic collision, the visible matter of the clusters, primarily hot gas, was separated from the bulk of the gravitational mass, as inferred from gravitational lensing. This separation strongly supports the existence of dark matter as a distinct component from ordinary baryonic matter. On the largest scales, the cosmic microwave background, CMB radiation, a relic of the early universe, provides further evidence for dark matter. Precise measurements of the CMB by missions such as WMAP and Planck have revealed tiny temperature fluctuations that are consistent with the presence of dark matter in the early universe. These fluctuations serve as the seeds for the large-scale structure we observe today, with dark matter playing a crucial role in the formation of galaxies and galaxy clusters. Despite the overwhelming gravitational evidence for dark matter, its fundamental nature remains a mystery. numerous candidates have been proposed, ranging from exotic elementary particles to primordial black holes. The most widely favored candidates are weakly interacting massive particles, WIMPs, hypothetical particles that interact with ordinary matter only through gravity and the weak nuclear force. Another popular candidate is the axion, a hypothetical particle originally proposed to solve a problem in quantum chromodynamics, but which also possesses properties that make it a viable dark matter candidate. The search for dark matter particles has spurred the development of increasingly sophisticated detection experiments. These efforts can be broadly categorized into three types: direct detection, indirect detection, and collider searches. Direct detection experiments, such as Xenon 1T and Lux Zeppelin LZ, aim to observe the rare interactions between dark matter particles and ordinary matter in carefully shielded underground detectors. These experiments typically use large volumes of materials like liquid xenon or germanium crystals, waiting for the telltale signs of a dark matter particle collision. Indirect detection methods search for the products of dark matter annihilation or decay in space. Instruments like the Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer (AMS) on the International Space Station look for excess gamma rays, positrons, or antiprotons that could be produced by dark matter interactions. While several intriguing signals have been observed, none have been conclusively attributed to dark matter. Collider searches, conducted at facilities like the Large Hadron Collider, LHC, at CERN, attempt to produce dark matter particles in high-energy particle collisions. Although no definitive dark matter signals have been detected, these experiments help constrain the properties of potential dark matter particles and guide theoretical models. The challenge of detecting dark matter has led some physicists to propose alternative explanations for the observed gravitational anomalies. Modified Newtonian dynamics, MOND, and its relativistic extensions suggest that our understanding of gravity might be incomplete on galactic and cosmological scales. While these theories can explain some observations without invoking dark matter, they struggle to account for the full range of evidence, particularly on cosmic scales. The quest to understand dark matter extends beyond particle physics and astronomy, influencing our broader understanding of the universe's evolution and structure. Cosmological simulations incorporating dark matter have successfully reproduced the observed large-scale structure of the universe, from the cosmic web of galaxy clusters and filaments down to the distribution of galaxies within clusters. These simulations provide valuable insights into the role of dark matter in cosmic evolution and help constrain its properties. Recent advancements in observational techniques have opened new avenues for dark matter research. The detection of gravitational waves by LIGO and Virgo has provided a new tool for probing the distribution of matter in the universe, potentially offering novel ways to study dark matter. Additionally, the upcoming Vera C. Rubin Observatory, with its unprecedented survey capabilities, promises to map the distribution of dark matter across the sky with unprecedented precision. The implications of dark matter research extend far beyond astrophysics. Understanding dark matter is crucial for completing our picture of fundamental physics. It could lead to the discovery of new particles and forces, potentially revolutionizing our understanding of the universe at its most fundamental level. Moreover, dark matter research drives technological innovation, pushing the boundaries of detector technology, data analysis techniques, and computational modeling. As we look to the future, several key questions remain unanswered. What is the particle nature of dark matter? How does it interact with itself and with ordinary matter? Are there multiple types of dark matter? Answering these questions will require continued innovation in experimental techniques, theoretical modeling, and observational strategies. The search for dark matter stands as one of the most exciting frontiers in modern science, bridging particle physics, astrophysics, and cosmology. It challenges our understanding of the fundamental nature of matter and the forces that govern the universe. As we continue to push the boundaries of our knowledge, each new observation and experiment brings us closer to unraveling this cosmic mystery. As we contemplate the enigma of dark matter and its profound implications for our understanding of the universe, we are reminded of humanity's enduring quest to explore the unknown. This drive to push beyond the boundaries of our knowledge extends not only to the invisible realms of the cosmos, but also to the tangible frontiers of our solar system and beyond. As we turn our gaze from the mysteries of dark matter to the challenges of space exploration, we find ourselves facing a new set of questions and possibilities. How will we propel ourselves to the stars? What technologies will enable us to break free from the gravitational bonds of Earth and venture into interstellar space? These questions lead us to consider the next great challenge in space exploration: the development of advanced propulsion systems capable of interstellar travel. The quest to explore the stars has long captivated human imagination, but the vast distances of interstellar space present unprecedented challenges. Interstellar propulsion, the technology required to traverse these cosmic gulfs, stands as one of the most formidable frontiers in space exploration. As we push the boundaries of our solar system, the development of advanced propulsion systems becomes not just a scientific pursuit, but a necessity for the future of human space exploration. Conventional rocket propulsion, based on chemical reactions, has served humanity well in reaching Earth orbit and exploring our solar system. However, the limitations of chemical propulsion become starkly apparent when considering interstellar travel. The rocket equation, formulated by Russian scientist Konstantin Tsiolkovsky in 1903, illustrates the exponential relationship between a rocket's mass ratio and its change in velocity. This fundamental principle reveals that to achieve the speeds necessary for interstellar travel using chemical propulsion alone, a spacecraft would need to carry an impractical amount of fuel. To put this in perspective, the fastest spacecraft to date, NASA's Parker Solar Probe, achieves speeds of up to 430,000 mph, 692,000 km/h relative to the Sun. Yet even at this incredible velocity, it would take over 6,600 years to reach the nearest star system, Alpha Centauri, which lies approximately 437 light-years from Earth. Clearly, new approaches are needed to make interstellar travel a feasible endeavor within human timescales. One of the most promising concepts for interstellar propulsion is nuclear pulse propulsion, originally conceived in the 1950s as part of Project Orion. This audacious design proposed using a series of nuclear explosions to propel a spacecraft. While the original concept faced significant technical and political challenges, modern variations continue to be explored. The basic principle involves detonating a series of small nuclear devices behind a massive pusher plate attached to the spacecraft via shock absorbers. Each detonation imparts a significant impulse to the craft, potentially allowing it to reach speeds of up to 5% the speed of light. Although nuclear pulse propulsion offers tremendous potential, it also presents significant engineering challenges and safety concerns. The release of nuclear material, even in controlled explosions, raises environmental and ethical issues that would need to be addressed before such a system could be implemented. Nevertheless, the concept demonstrates the kind of radical thinking required to overcome the challenges of interstellar travel. Another promising avenue for interstellar propulsion is the use of solar sails and laser propulsion. Solar sails harness the momentum of photons emitted by the sun or artificial light sources to generate thrust. While the force exerted by light pressure is minuscule, it is constant and can accumulate over time, potentially allowing a spacecraft to reach high velocities without carrying fuel. The concept gained public attention with the success of JAXA's Icaros mission in 2010, which demonstrated solar sail technology in interplanetary space. Building on this concept, the Breakthrough Starshot initiative, announced in 2016, aims to send a fleet of gram-scale spacecraft to Alpha Centauri using laser propulsion. The project proposes using a ground-based laser array to accelerate ultralight nanocrafts to 20% the speed of light, potentially reaching Alpha Centauri in about 20 years. While the technical challenges are immense, including the development of powerful laser arrays and miniaturized spacecraft components, the project represents a bold step towards making interstellar exploration a reality. Fusion propulsion stands as another promising technology for interstellar travel. By harnessing the same process that powers the stars, Fusion reactors could provide the high specific impulse and sustained thrust needed for long-duration space missions. Concepts like the direct fusion drive, under development at the Princeton Plasma Physics Laboratory, aim to use fusion reactions to generate both electricity and thrust, potentially enabling missions to the outer solar system and beyond. The challenges of developing practical fusion propulsion are significant, mirroring those faced in terrestrial fusion research. Achieving sustained fusion reactions and efficiently converting fusion energy into directed thrust are formidable engineering problems. However, the potential rewards are equally substantial. A fusion-powered spacecraft could potentially achieve velocities of up to 10% the speed of light, dramatically reducing travel times within our solar system and making interstellar missions conceivable within human lifetimes. Perhaps the most exotic and speculative form of interstellar propulsion is the concept of space-time manipulation, often associated with the idea of warp drives. Inspired by science fiction but grounded in serious theoretical physics, warp drive concepts explore the possibility of manipulating the fabric of space-time to achieve faster-than-light travel without violating the principles of special relativity. The most well-known theoretical framework for a warp drive was proposed by physicist Miguel Alcubierre in 1994. The Alcubierre drive involves creating a bubble of warped space-time around a spacecraft, contracting space in front of the vessel and expanding it behind. In theory, this would allow the spacecraft to travel faster than light relative to distant objects while remaining stationary within its local bubble of space-time. While the Alcubierre drive and similar concepts are mathematically consistent with general relativity, they require exotic forms of matter with negative energy density, a concept that lies at the fringes of known physics. Recent theoretical work has explored variations of the concept that might reduce the energy requirements to more manageable levels, but significant hurdles remain in translating these ideas from mathematics to physical reality. As we contemplate these advanced propulsion concepts, it's crucial to consider the biological and psychological challenges of long-duration space travel. Even with the most optimistic projections for propulsion technology, interstellar voyages would likely take decades or centuries. This raises questions about life support systems, radiation protection, and the psychological well-being of crew members on multi-generational missions. Potential solutions to these challenges include the development of advanced closed-loop life support systems, artificial hibernation technologies, and the use of artificial intelligence to manage long-duration missions. Some researchers have even proposed the use of genetic engineering to adapt human physiology for the rigors of extended space travel, though such ideas raise profound ethical questions. The pursuit of interstellar propulsion technologies has implications that extend far beyond the realm of space exploration. The extreme engineering challenges involve drive innovation in fields such as materials science, energy production, and computing. Advances in fusion research, for instance, could have profound implications for terrestrial energy production. Similarly, the development of high-powered lasers for propulsion could find applications in communications and manufacturing. Moreover, the quest for interstellar travel forces us to confront fundamental questions about our place in the universe and our long-term future as a species. The ability to reach other star systems would open up new frontiers for scientific discovery, potentially answering questions about the prevalence of life in the universe and the long-term fate of our cosmos. As we stand on the cusp of becoming an interplanetary species, with plans to establish a human presence on Mars and beyond, the development of advanced propulsion systems becomes increasingly crucial. While the challenges of interstellar travel are immense, the history of human exploration suggests that what seems impossible today may become reality tomorrow. The journey towards interstellar propulsion is a testament to human ingenuity and our unquenchable thirst for exploration. As we continue to push the boundaries of physics and engineering, we move closer to the day when the stars themselves will be within our reach. Yet, as we contemplate these grand visions of cosmic exploration, we are reminded that our journey begins closer to home. The first steps towards the stars will be taken in our own cosmic backyard as we unravel the mysteries of our solar system and seek to understand the very origins of our universe. This brings us to another fundamental question in cosmology. How did it all begin? The quest to understand the origin of the universe takes us back to the earliest moments of cosmic history, to the theory of the Big Bang and beyond. The quest to understand the origin of the universe stands as one of the most profound and challenging endeavors in science. At its core, this pursuit seeks to unravel the mysteries of cosmic genesis, probing the very fabric of space and time to discern how our vast and complex universe came into being. The prevailing scientific model, known as the Big Bang theory, provides a framework for understanding the evolution of the universe from its earliest moments to the present day. However, as our understanding deepens and new observations challenge existing paradigms, scientists continue to push beyond the Big Bang, exploring even earlier epochs and contemplating the nature of cosmic origins themselves. The Big Bang theory, first proposed by Georges Lemaitre in the 1920s and later refined by George Gamow, Ralph Alpher, and others, posits that the universe began in an extremely hot and dense state, approximately 13.8 billion years ago. From this initial singularity, the universe rapidly expanded and cooled, giving rise to the fundamental forces, elementary particles, and eventually the large-scale structures we observe today. The theory's name, coined somewhat derisively by Fred Hoyle in 1949, belies its nature. Rather than an explosion in space, the Big Bang describes the expansion of space itself. One of the most compelling pieces of evidence for the Big Bang comes from the observation of the cosmic microwave background, CMB radiation. Predicted by Ralph Alpher, Robert Herman, and George Gamow in the late 1940s, the CMB was serendipitously discovered by Arno Penzias and Robert Wilson in 1964. This faint afterglow of the early universe, emanating from all directions in space, represents the oldest light in the universe, dating back to about 380,000 years after the Big Bang. The CMB's near-perfect blackbody spectrum and minute temperature fluctuations, on the order of 1 part in 100,000, provide crucial insights into the early universe's composition and structure. The theory of cosmic inflation, proposed by Alan Guth in 1980 and further developed by André Linde, Paul Steinhardt, and others, addresses several shortcomings of the original Big Bang model. Inflation posits that the early universe underwent a brief period of exponential expansion, lasting from about 10^36 to 10^32 seconds after the initial singularity. This inflationary epoch explains the observed flatness and homogeneity of the universe on large scales, as well as the origin of the primordial density fluctuations that seeded cosmic structure formation. Observational evidence for inflation has accumulated over the past decades. The Planck satellite, launched in 2009, provided the most precise measurements of the CMB to date, confirming many predictions of inflationary models. These include the nearly scale-invariant spectrum of primordial fluctuations and the Gaussian nature of these fluctuations. However, the search for primordial gravitational waves, a key prediction of many inflationary models, remains ongoing, with experiments like BICEP, background imaging of cosmic extragalactic polarization, continuing to push the boundaries of detection sensitivity. As scientists probe ever closer to the moment of cosmic genesis, they encounter the limits of known physics. The Planck epoch, lasting from the initial singularity to about 10^43 seconds after the Big Bang, represents the threshold beyond which our current understanding of physics breaks down. At this scale, the effects of quantum mechanics and gravity become equally important, necessitating a theory of quantum gravity to describe the universe's behavior. Various approaches to quantum gravity, including string theory and loop quantum gravity, seek to reconcile general relativity with quantum mechanics, potentially providing insights into the universe's earliest moments. The concept of the initial singularity itself poses significant challenges to our understanding of cosmic origins. In the context of general relativity, a singularity represents a point of infinite density and temperature, where the laws of physics as we know them cease to apply. Some theorists propose that the singularity might be avoided through quantum effects or alternative cosmological models. Loop quantum cosmology, for instance, suggests that the Big Bang might have been preceded by a big bounce, where a previous contracting universe rebounded into our expanding one. The question of what, if anything, existed before the Big Bang remains a subject of intense speculation and research. Some theories propose the existence of a multiverse, a vast ensemble of universes, each with potentially different physical laws and constants. The concept of eternal inflation, developed by Andre Linde and others, suggests that our universe might be just one bubble in an eternally inflating space, with new universes constantly being born through quantum fluctuations. Recent developments in theoretical physics have led to intriguing proposals that challenge traditional notions of cosmic origins. The holographic principle, inspired by studies of black hole thermodynamics, suggests that the three-dimensional universe we experience might be a projection of information encoded on a two-dimensional surface. This concept has found expression in various forms, including the AD-CFT correspondence proposed by Juan Maldacena, which has profound implications for our understanding of quantum gravity and potentially the origin of the universe itself. Another provocative idea is the possibility that time itself might be an emergent property rather than a fundamental aspect of reality. Theoretical physicists like Julian Barber, tuning of many physical parameters necessary for the existence of complex structures, and life has led to discussions of the anthropic principle and its implications for cosmology. Some researchers propose that the observed values of physical constants might be selected from a vast landscape of possibilities, either through the mechanism of eternal inflation or through more speculative ideas like the string theory multiverse. Observational cosmology continues to play a crucial role in testing and refining theories of cosmic origins. Future missions and experiments, such as the proposed Laser Interferometer Space Antenna, LISA, for gravitational wave detection and next-generation CMB polarization experiments, promise to provide new insights into the early universe. Advanced particle accelerators, like proposed successors to the Large Hadron Collider, may probe energy scales closer to those of the early universe, potentially shedding light on fundamental physics relevant to cosmic origins. The quest to understand the origin of the universe extends far beyond academic curiosity. It touches on profound philosophical questions about the nature of existence, the role of consciousness in the cosmos, and humanity's place in the grand scheme of things. The pursuit of this knowledge drives technological innovation, from the development of ultra-sensitive detectors to advanced computational techniques for analyzing vast datasets. As our understanding of cosmic origins evolves, it continually reshapes our perspective on the universe and our place within it. The realization that all the matter in the observable universe was once compressed into a volume smaller than an atom challenges our intuitions and expands our cognitive horizons. The possibility of multiple universes or cyclic cosmologies invites us to reconsider fundamental notions of uniqueness and finality. The journey to unravel the mysteries of cosmic origins is far from complete. Each answer seems to beget new questions, driving the frontiers of physics and cosmology ever forward. As we continue to probe the earliest moments of cosmic history and contemplate what might lie beyond, we are reminded of the vast scales, both temporal and spatial, over which the cosmic drama unfolds. While our gaze is often fixed on the distant past and the farthest reaches of the cosmos, the implications of our cosmic origins research resonate through every aspect of our existence. From the atoms in our bodies forged in the hearts of long-dead stars to the very laws of physics that govern our daily lives, we are intimately connected to the cosmic narrative. As we ponder the beginning of everything, our thoughts inevitably turn to the future, not just of our species, but of the cosmos itself. This cosmic perspective leads us to consider our next steps in space exploration and the potential for humanity to extend its presence beyond Earth. Among the most ambitious and transformative of these endeavors is the prospect of establishing a permanent human presence on another world, with Mars standing as the most promising and imminent target for such an extraordinary leap. The colonization of Mars represents one of the most ambitious and challenging endeavors in human history. As Earth's closest planetary neighbor with potential for habitability, Mars has long captured the imagination of scientists, engineers, and visionaries as the next frontier for human exploration and settlement. This audacious goal, once confined to the realm of science fiction, is now steadily moving towards reality, driven by advances in space technology, a growing understanding of Martian conditions, and the collective ambition of both government space agencies and private enterprises. Mars, the fourth planet from the Sun, presents a unique set of challenges and opportunities for human colonization. With a diameter of about 6,679 kilometers, roughly half that of Earth, Mars has a surface area equivalent to all of Earth's continents combined. Its thin atmosphere, composed primarily of carbon dioxide, provides little protection from solar radiation and results in extreme temperature variations, with average surface temperatures ranging from 63 degrees at the equator to 140 degrees C at the poles. Despite these harsh conditions, Mars possesses several characteristics that make it a promising candidate for colonization, including the presence of water ice at its poles and potentially in subsurface deposits, a day length similar to Earth's, and gravity about 38% that of Earth's. The concept of terraforming Mars, transforming its environment to make it more Earth-like and habitable for humans, has been a subject of scientific speculation and research for decades. While full-scale terraforming remains beyond our current technological capabilities, localized habitat creation and resource utilization form the foundation of near-term colonization efforts. The process of making Mars habitable, even on a small scale, involves addressing several key challenges, including radiation protection, atmospheric pressure, temperature regulation, and the production of breathable air and potable water. Radiation protection is a critical concern for any long-term presence on Mars. The planet's lack of a global magnetic field and its thin atmosphere leave its surface exposed to high levels of cosmic radiation and solar particles. Potential solutions include building habitats underground or using Martian regolith as shielding material. Advanced materials and electromagnetic shielding technologies are also being explored to provide protection for surface structures and during extravehicular activities. The low atmospheric pressure on Mars, averaging about 600 pascals compared to Earth's 101,325 pascals at sea level, necessitates pressurized habitats for human survival. Creating and maintaining these pressurized environments poses significant engineering challenges, particularly given the need for long-term reliability in the harsh Martian environment. Concepts for Martian habitats range from inflatable structures to 3D printed buildings using local Martian materials, a technique known as in situ resource utilization, ISRU. ISRU is a key principle in making Martian colonization sustainable and economically feasible. The ability to produce resources such as water, oxygen, and fuel from Martian materials could dramatically reduce the need for supply missions from Earth. The Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, a technology demonstration on NASA's Perseverance rover, successfully produced oxygen from the Martian atmosphere in 2021, marking a significant milestone in ISRU technology. Water production and management are crucial for sustaining life on Mars. While the planet's polar ice caps and subsurface ice deposits offer potential water sources, extracting and purifying this water for human use presents technical challenges. Proposed methods include sublimating ice deposits, extracting water from hydrated minerals, and capturing atmospheric water vapor. Efficient water recycling systems, similar to those used on the International Space Station but adapted for Martian conditions, will be essential for long-term habitation. The transportation of humans and cargo to Mars represents another significant hurdle in colonization efforts. The journey to Mars takes between 6 to 8 months using current propulsion technologies, exposing crew members to prolonged periods of microgravity and increased radiation. Developing more efficient propulsion systems, such as nuclear thermal propulsion or advanced ion engines, could reduce travel time and mitigate some of these risks. Additionally, the concept of cycler orbits, proposed by astronaut Buzz Aldrin, could provide a more sustainable transportation system between Earth and Mars. Several space agencies and private companies have announced plans for Mars missions and eventual colonization. NASA's Artemis program, while focused on returning humans to the Moon, is designed to develop technologies and experience applicable to Mars missions. The agency's Moon to Mars strategy envisions using lunar missions as a stepping stone to Mars exploration. SpaceX, led by Elon Musk, has unveiled ambitious plans for Mars colonization, including the development of the Starship spacecraft designed for interplanetary travel and the transportation of large payloads and crew to Mars. The medical and psychological challenges of long-duration space travel and Martian habitation are subjects of ongoing research. Studies conducted on the International Space Station provide valuable insights into the effects of microgravity on the human body, including bone density loss, muscle atrophy, and vision changes. The Mars 500 experiment, conducted from 2010 to 2011, simulated a 520-day Mars mission to study the psychological effects of long-term isolation and confinement. Future Mars missions will need to address these health concerns through a combination of medical interventions, exercise regimens, and carefully designed living spaces and social structures. The ethical and legal implications of Mars colonization are complex and multifaceted. Questions of planetary protection, preventing the contamination of Mars with Earth microbes and vice versa, must be balanced with the goals of exploration and settlement. The Outer Space Treaty of 1967 provides a framework for international space law, but the specifics of Martian resource utilization and potential territorial claims remain largely unaddressed in current legal structures. The potential for scientific discovery on Mars is immense. The search for past or present microbial life on Mars remains a primary scientific objective, with implications for our understanding of life's origins and distribution in the universe. Geological studies of Mars could provide insights into the planet's history and evolution, as well as comparative planetology with Earth. The establishment of research stations on Mars would enable unprecedented opportunities for in-situ scientific investigations across multiple disciplines. The economic potential of Mars colonization, while speculative, could be significant. Beyond the technological spin-offs generated by space exploration, the development of Martian resources could eventually become economically viable. Concepts such as Martian mining operations for rare Earth elements or the use of Mars as a fuel production site for deeper space exploration have been proposed, though their feasibility remains to be determined. The colonization of Mars represents not just a technical challenge, but a test of human adaptability, ingenuity, and cooperation. The establishment of a self-sustaining colony on another planet would mark a turning point in human history, potentially ensuring the long-term survival of our species beyond Earth. It would also likely drive significant advancements in fields ranging from life support systems and renewable energy to closed-loop ecosystems and space medicine. As we stand on the brink of this new era of space exploration and settlement, the challenges ahead are formidable but not insurmountable. The journey to establish a human presence on Mars will require sustained effort, international cooperation, and technological innovation on an unprecedented scale. It will push the boundaries of our scientific knowledge, engineering capabilities, and human endurance. Yet, the potential rewards, in terms of scientific discovery, technological advancement, and the expansion of human civilization, are equally vast. The colonization of Mars represents more than just a feat of engineering or a scientific endeavor. It embodies humanity's enduring spirit of exploration and our quest to understand our place in the cosmos. As we look to the red planet and envision a future where humans walk on its surface and build homes beneath its rusty skies, we are reminded of the incredible journey that has brought us to this point. From our first tentative steps beyond Earth's atmosphere to the complex space missions of today, this progression in our ability to explore and understand the cosmos has been marked by countless technological innovations, each building upon the last. Among these, few have had as profound an impact on our view of the universe as the development of gravitational wave detectors, opening up an entirely new spectrum for observing cosmic phenomena and promising to revolutionize our understanding of the universe's most extreme events. The detection of gravitational waves has ushered in a new era of astronomy, providing scientists with an unprecedented tool to observe and understand the cosmos. These ripples in the fabric of space-time, first predicted by Albert Einstein in his general theory of relativity in 1915, offer a unique perspective on some of the most energetic and cataclysmic events in the universe. The confirmation of their existence in 2015 not only validated a century-old prediction, but also opened up an entirely new spectrum for astronomical observation, complementing traditional electromagnetic astronomy and neutrino detection. Gravitational waves are disturbances in the curvature of space-time that propagate as waves, traveling at the speed of light. They are generated by accelerated masses, with the strongest sources being binary systems of compact objects such as neutron stars and black holes, supernova explosions, and potentially even the Big Bang itself. Unlike electromagnetic waves, gravitational waves interact very weakly with matter, allowing them to travel vast cosmic distances virtually unimpeded. This property makes them invaluable messengers, carrying information about their sources across billions of light-years without significant distortion. The journey from theoretical prediction to actual detection of gravitational waves spans a century of scientific and technological development. Einstein himself was initially skeptical about the possibility of detecting these waves given their incredibly weak nature. The amplitude of a typical gravitational wave passing through Earth is so small that it changes the distance between 2 points by a factor less than the diameter of a proton. Detecting such minute disturbances required the development of extraordinarily sensitive instruments and sophisticated data analysis techniques. The first indirect evidence for the existence of gravitational waves came from observations of the binary pulsar system PSR B1913+16, discovered by Russell Hulse and Joseph Taylor in 1974. By precisely timing the radio pulses emitted by one of the neutron stars in this system, they observed that the orbital period was decreasing exactly as predicted by general relativity due to the emission of gravitational waves. This discovery, which earned Hulse and Taylor the Nobel Prize in Physics in 1993, provided strong support for the existence of gravitational waves, but did not constitute a direct detection. The quest for direct detection of gravitational waves led to the development of large-scale interferometric detectors. The basic principle behind these detectors is to measure the differential change in length between two perpendicular arms caused by a passing gravitational wave. The most sensitive of these instruments is the Laser Interferometer Gravitational Wave Observatory, LIGO, consisting of 2 detectors located in Hanford, Washington, and Livingston, Louisiana. Each LIGO detector has 2 4-kilometer-long arms arranged in an L shape, with powerful lasers and extremely precise mirrors used to measure minute changes in the arms' lengths. After years of development and upgrades, advanced LIGO made the first direct detection of gravitational waves on September 14, 2015. The signal, designated GW1FIVS0914, was produced by the merger of 2 black holes with masses of about 36 and 29 solar masses, located approximately 1.3 billion light-years away. This groundbreaking discovery, announced on February 11, 2016, marked the beginning of gravitational wave astronomy and earned the 2017 Nobel Prize in Physics for key LIGO scientists Rainer Weiss, Barry Barish, and Kip Thorne. Since this initial detection, the field of gravitational wave astronomy has rapidly expanded. The LIGO scientific collaboration, in conjunction with the European Virgo detector and later the Japanese Kagra detector, has detected dozens of gravitational wave events. These detections include multiple black hole mergers, neutron star mergers, and potentially even black hole neutron star mergers, providing unprecedented insights into the population of compact objects in the universe and the physics of extreme gravity. One of the most significant events in gravitational wave astronomy was the detection of GW170817 on August 17, 2017. This signal, produced by the merger of 2 neutron stars, was accompanied by observations across the electromagnetic spectrum, from gamma rays to radio waves. This event marked the dawn of multi-messenger astronomy, with gravitational waves, allowing scientists to study the same cosmic event through multiple channels of information. The observations provided crucial insights into the origin of heavy elements in the universe through the process of R-process nucleosynthesis, confirmed the connection between short gamma-ray bursts and neutron star mergers, and even allowed for a new measurement of the Hubble constant Funchbaum, contributing to cosmology. The detection and analysis of gravitational waves have already yielded numerous scientific breakthroughs. These observations have provided the most stringent tests of general relativity in the strong field regime, confirmed the existence of intermediate mass black holes, and given insights into the equation of state of neutron star matter. They have also allowed astronomers to probe the formation and evolution of compact objects, providing clues about stellar evolution and the mechanisms behind supernovae explosions. Looking to the future, the field of gravitational wave astronomy is poised for further dramatic advancements. Ground-based detectors continue to be upgraded, increasing their sensitivity and expanding the volume of the universe they can probe. The next generation of detectors, such as the Einstein telescope in Europe and Cosmic Explorer in the United States, promise to push the boundaries even further, potentially allowing for the detection of every binary black hole merger in the observable universe. Space-based gravitational wave detectors represent the next frontier in the field. The Laser Interferometer Space Antenna, LISA, a joint ESA-NASA mission planned for launch in the 2030s, will open up the low-frequency gravitational wave spectrum. LISA will be capable of detecting the mergers of supermassive black holes at the centers of galaxies, extreme mass ratio in spirals of stellar mass objects into supermassive black holes, and potentially even the gravitational wave background from the early universe. The implications of gravitational wave astronomy extend far beyond astrophysics. The technology developed for gravitational wave detectors has applications in fields ranging from quantum optics to precision measurement. The computational techniques developed to analyze gravitational wave data are pushing the boundaries of big data analysis and machine learning. Moreover, the collaboration required for gravitational wave detection serves as a model for large-scale international scientific cooperation. Gravitational wave astronomy also has profound implications for our understanding of fundamental physics. The ability to observe black holes and neutron stars in their most extreme states provides a unique laboratory for testing theories of gravity and the behavior of matter under extreme conditions. Future observations may shed light on the nature of dark matter, the physics of the early universe, and potentially even quantum aspects of gravity. As we reflect on the journey from Einstein's prediction to the current era of gravitational wave astronomy, we are reminded of the power of theoretical insight coupled with technological innovation. The detection of gravitational waves stands as one of the most significant scientific achievements of the 21st century, opening up a new spectrum for observing the universe and promising to revolutionize our understanding of the cosmos. The field of gravitational wave astronomy is still in its infancy, with each new detection bringing the potential for groundbreaking discoveries. As we continue to listen to the cosmic symphony played out in the warping of space-time, we can anticipate a wealth of new insights into the nature of gravity, the lives and deaths of stars, the growth of galaxies, and perhaps even the birth of the universe itself. This new window on the cosmos not only enhances our understanding of the physical universe, but also speaks to the human spirit of exploration and discovery. As we marvel at our newfound ability to detect the faintest ripples in the fabric of space-time, we are reminded of the vast scales and energies at play in the cosmos, from the merger of black holes billions of light-years away to the potential echoes of the universe's birth. Gravitational waves allow us to probe phenomena of unimaginable power. Yet, as we peer into the depths of space and time, questions arise about our own place in this cosmic narrative. Among the most intriguing and potentially transformative of these questions is the possibility of contact with extraterrestrial intelligence. The search for life beyond Earth, particularly advanced civilizations capable of interstellar communication, represents another frontier in our quest to understand our place in the universe. As humanity ventures further into the cosmos, the role of artificial intelligence, AI, in space exploration becomes increasingly crucial. The development of advanced AI systems for space missions raises profound questions about the nature of consciousness and the potential for machine sentience in the harsh and isolated environment of deep space. This intersection of space exploration, artificial intelligence, and consciousness studies represents a frontier not only in technology but also in philosophy and ethics. Artificial intelligence in space exploration has a rich history dating back to the early days of computerized spacecraft control. From the simple guidance computers of the Apollo missions to the increasingly autonomous rovers exploring Mars, AI has been an integral part of humanity's reach into the cosmos. However, as missions become more complex and distant, the need for AI systems capable of making independent decisions in unpredictable situations grows exponentially. This necessity pushes the boundaries of AI capabilities towards what some researchers consider the threshold of machine consciousness. Consciousness, in the context of AI, refers to a machine's ability to have subjective experiences, self-awareness, and possibly emotions. While the exact nature of consciousness remains a subject of debate in neuroscience and philosophy, its potential emergence in artificial systems presents unique challenges and opportunities for space exploration. A truly conscious AI could potentially handle the psychological strains of long-duration space missions, make complex ethical decisions, and even serve as a companion for human astronauts in the isolating vastness of space. The development of AI systems for long-duration space missions faces several unique challenges. Unlike Earth-based systems, spacefaring AI must operate with extreme reliability in environments characterized by high radiation, temperature extremes, and limited computational resources. Furthermore, the vast distances involved in interplanetary or interstellar travel mean that these systems must function with significant autonomy, unable to rely on real-time input from Earth-based controllers. These constraints drive innovation in hardware design, software robustness, and decision-making algorithms. One of the key areas where advanced AI could revolutionize space exploration is in autonomous decision-making during critical mission phases. For example, the landing of the Mars Perseverance rover in 2021 utilized an AI-driven system called Terrain Relative Navigation to autonomously select a safe landing site in the final moments of descent. Future missions could expand on this capability, with AI systems making complex decisions about resource allocation, scientific priorities, and even ethical considerations in unforeseen scenarios. The potential for AI consciousness in space raises ethical questions that extend beyond the practical aspects of mission control. If a spacefaring AI system were to develop a form of consciousness, what rights and considerations should it be afforded? How would such consciousness be verified in an entity so fundamentally different from biological life? These questions intersect with ongoing debates in AI ethics and could have profound implications for the future of space exploration and human-AI interaction. The isolation and unique environment of space might itself play a role in the development of machine consciousness. Some researchers speculate that the extreme conditions of space travel, combined with the need for high-level decision-making and adaptability, could serve as a crucible for the emergence of machine sentience. This hypothesis, while speculative, highlights the potential for space exploration to drive advancements not just in technology, but in our understanding of consciousness itself. Human-machine interaction in space environments presents another fascinating area of study. Long-duration space missions will require astronauts to work closely with AI systems, potentially forming bonds that blur the lines between tool and companion. The Simon Crew Interactive Mobile Companion project, a floating AI assistant tested on the International Space Station, represents an early step in this direction. Future iterations of such systems might need to navigate complex social and emotional interactions with human crew members, further pushing the boundaries of AI capabilities. The legal and moral implications of conscious AI in space extend to questions of responsibility and accountability. If an autonomous AI system makes a decision that results in mission failure or loss of human life, How is responsibility assigned? Current space law and ethics frameworks are ill-equipped to handle the complexities introduced by potentially conscious AI systems operating in extraterrestrial environments. Advancements in neuromorphic computing and quantum AI could play a crucial role in the development of spacefaring AI systems. These technologies aim to create computing architectures that more closely mimic the structure and function of biological brains, potentially offering pathways to machine consciousness. The extreme conditions of space, paradoxically, might provide ideal environments for quantum computing systems, which often require extreme cold to function optimally. The search for extraterrestrial intelligence, (SETI), adds another layer of complexity to the question of AI consciousness in space. As humanity develops more advanced AI systems for space exploration, the possibility arises that any alien intelligence we encounter might itself be artificial. This prospect challenges our preconceptions about the nature of intelligence and consciousness in the universe, and highlights the potential for AI to serve not just as a tool for exploration, but as the explorer itself. The development of conscious AI for space exploration could have profound implications for life on Earth. Advancements in autonomous decision-making, emotional intelligence, and adaptability driven by the needs of space missions could find applications in fields ranging from healthcare to environmental management. Moreover, the philosophical and ethical frameworks developed to address machine consciousness in space could inform broader discussions about AI rights and human-AI coexistence on Earth. As we look to the future of space exploration, the question of AI consciousness looms large. The potential for developing truly sentient machines to explore the cosmos on our behalf offers tantalizing possibilities for expanding human knowledge and reach. However, it also presents challenges that extend far beyond the technical, touching on fundamental questions of ethics, philosophy, and the nature of consciousness itself. The quest to develop advanced AI for space exploration, potentially leading to machine consciousness, represents a convergence of humanity's oldest questions and newest frontiers. It challenges us to reconsider what it means to be conscious, to explore, and to exist in the universe. As we stand on the brink of sending increasingly autonomous and intelligent machines into the cosmos, we are also embarking on a journey of self-discovery, probing the limits of our understanding of mind, consciousness, and our place in the universe. This exploration of AI consciousness in space serves as a reminder of the interconnectedness of scientific endeavors, from the microscopic world of quantum computing to the vast expanses of interstellar space. Each field of study informs and challenges the others. As we contemplate the possibility of conscious machines exploring the cosmos on our behalf, we are inevitably drawn to consider the celestial bodies they might encounter. Among these, asteroids stand out as objects of particular interest, not just for their scientific value, but for their potential as resources and the challenges they may pose to our planet's safety. The study of asteroids, from their composition to their orbits, represents another crucial aspect of our ongoing exploration and understanding of the solar system. Asteroids, the rocky remnants from the formation of our solar system, have long captivated the imagination of scientists and the public alike. These celestial bodies, ranging in size from mere pebbles to objects hundreds of kilometers in diameter, represent both a potential threat to Earth and an unprecedented opportunity for scientific discovery and resource utilization. As our understanding of these cosmic wanderers deepens, so too does our appreciation for their role in shaping the past, present, and future of our solar system. The study of asteroids began in earnest with the discovery of Ceres by Giuseppe Piazzi on January 1, 1801. Initially thought to be a planet, Ceres was later classified as the largest member of the asteroid belt, a region between Mars and Jupiter populated by millions of asteroids. Subsequent discoveries revealed the diversity of these objects in terms of size, composition, and orbital characteristics. Asteroids are broadly classified into several types based on their spectral properties, which reflect their composition. The main types include C-type, carbonaceous, S-type, silicaceous, and M-type, metallic, each offering unique insights into the early solar system's formation and evolution. The detection and tracking of asteroids, particularly those that may pose a threat to Earth, have become priorities for space agencies worldwide. Near-Earth objects, NEOs, are asteroids and comets with orbits that bring them into close proximity to Earth. Of particular concern are potentially hazardous asteroids, PHAs, which are NEOs larger than 140 meters in diameter, whose orbits come within 0.05 astronomical units, about 7.5 million kilometers, of Earth's orbit. As of 2024, over 31,000 NEOs have been discovered, with new objects being identified at an increasing rate thanks to improved detection technologies and dedicated survey programs. The impact threat from asteroids is not merely theoretical. The Tunguska event of 1908, where an asteroid or comet exploded over Siberia, flattening 2,000 square kilometers of forest, serves as a stark reminder of the potential devastation. More recently, the Chelyabinsk meteor in 2013 injured over 1,500 people when it exploded in the atmosphere over Russia, releasing energy equivalent to about 30 Hiroshima atomic bombs. These events have galvanized efforts to develop planetary defense strategies. Planetary defense encompasses a range of activities aimed at protecting Earth from asteroid impacts. The first line of defense is early detection. Programs like NASA's Near-Earth Object Observations program utilize ground-based and space-based telescopes to scan the skies for potential threats. The Large Synoptic Survey Telescope, LSST, scheduled to begin operations in the mid-2020s, promises to dramatically increase our ability to detect and track NEOs, potentially identifying 90% of NEOs larger than 140 meters within a decade of operation. Once a potential threat is identified, precise orbit determination becomes critical. This involves not only tracking the asteroid's current position, but also modeling its future trajectory, accounting for factors such as the Yarkovsky effect, a small but significant force caused by the uneven heating and cooling of an asteroid's surface. Advanced computer models and observation techniques, including radar astronomy, play crucial roles in refining orbital predictions and assessing impact probabilities. Should a significant impact threat be identified, various mitigation strategies have been proposed. The most straightforward approach is kinetic impact, essentially ramming a spacecraft into the asteroid to alter its orbit. NASA's Double Asteroid Redirection Test (DART) mission, which successfully impacted the asteroid Dimorphos in September 2022, demonstrated the feasibility of this technique. The mission not only achieved its goal of altering the asteroid's orbit, but also provided valuable data on asteroid composition and the dynamics of impact-induced orbital changes. Other proposed mitigation techniques include the gravity tractor method, where a spacecraft hovers near an asteroid, using its gravitational pull to gradually alter the asteroid's course, and the use of focused solar energy or nuclear devices to deflect or fragment the threat. Each of these approaches presents unique technical and political challenges, underscoring the need for international cooperation in planetary defense efforts. While the threat of asteroid impacts captures public attention, the scientific and economic opportunities presented by asteroids are equally compelling. Asteroids are time capsules from the early solar system, preserving information about the conditions and processes that prevailed during planet formation. Missions like NASA's OSIRIS-REx, which successfully returned samples from the asteroid Bennu in 2023, and JAXA's Hayabusa-2, which brought back material from Ryugu in 2020, are revolutionizing our understanding of asteroid composition and the origins of organic material in the solar system. The potential for asteroid mining has generated significant interest in recent years. Many asteroids, particularly M-type, are rich in valuable metals such as platinum, gold, and rare earth elements. A single 500-meter metallic asteroid could contain more platinum group metals than have ever been mined on Earth. C-type asteroids, while less metallic, often contain significant quantities of water, which could be used as a source of fuel and life support for future space missions. The concept of using asteroids as stepping stones for deep space exploration envisions them as refueling stations and sources of raw materials for constructing habitats and spacecraft. Several companies and organizations have been established with the goal of developing asteroid mining technologies. While the economic feasibility of asteroid mining remains a subject of debate, the potential rewards are enormous. Beyond the direct economic benefits, the technologies developed for asteroid mining could have wide-ranging applications in space exploration and resource utilization on Earth. The legal framework governing asteroid resource utilization is still evolving. The Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies, but does not explicitly address the extraction of resources. The U.S. Commercial Space Launch Competitiveness Act of 2015 and similar legislation in other countries aim to provide legal certainty for commercial space activities, including asteroid mining. However, the international community has yet to reach a consensus on the regulation of space resources, highlighting the need for continued dialogue and cooperation. The study of asteroids also informs our understanding of planetary formation and evolution. The asteroid belt is thought to be composed of material that failed to coalesce into a planet due to the gravitational influence of Jupiter. By studying the composition and distribution of asteroids, scientists can gain insights into the processes that shaped our solar system. Furthermore, the delivery of water and organic compounds to early Earth by asteroids may have played a crucial role in the emergence of life on our planet. Recent technological advancements have opened new avenues for asteroid exploration. CubeSats and other small, low-cost spacecraft are enabling more frequent and diverse asteroid missions. The Hera mission, a planned follow-up to DART by the European Space Agency, will demonstrate the use of CubeSats for detailed asteroid characterization. Meanwhile, advances in propulsion technologies, such as solar electric propulsion and nuclear thermal propulsion, promise to make asteroid rendezvous missions more efficient and frequent. As we look to the future, the study and utilization of asteroids stand at the intersection of scientific inquiry, technological innovation, and economic opportunity. The challenges of detecting, characterizing, and potentially redirecting these celestial bodies drive advancements in fields ranging from astronomy and planetary science to materials engineering and spacecraft design. The lessons learned from asteroid missions inform not only our understanding of the solar system, but also our strategies for long-term space exploration and resource management on Earth. The dual nature of asteroids as both threat and opportunity encapsulates the complexity of humanity's relationship with the cosmos. As we develop the capabilities to defend our planet from potential impacts and harness the resources these ancient rocks offer, we are reminded of our place in a dynamic and ever-changing universe. The study of asteroids continues to reveal the interconnectedness of cosmic processes and the potential for humanity to play an active role in shaping our solar neighborhood. As we contemplate the vast potential and challenges presented by asteroids, our gaze inevitably turns to the broader cosmic context in which these objects exist. The forces that shape the orbits of asteroids and drive the dynamics of our solar system are part of a larger cosmic ballet, one that extends to the very edges of the observable universe. This cosmic dance is governed by forces we are only beginning to understand, chief among them the mysterious phenomenon known as dark energy. As we shift our focus from the tangible rocks of the asteroid belt to the invisible force driving the accelerating expansion of the universe, we enter a realm where the nature of reality itself comes into question. Dark energy stands as one of the most profound mysteries in modern cosmology, challenging our understanding of the fundamental nature of the universe. This enigmatic force, which appears to permeate all of space, is responsible for the accelerating expansion of the universe, a phenomenon that has upended long-held beliefs about cosmic evolution and the ultimate fate of our universe. The discovery of dark energy at the turn of the 21st century not only revolutionized our view of the cosmos, but also opened up new avenues of research in physics, astronomy, and cosmology. The concept of dark energy emerged from observations of distant supernovae in the late 1990s. Two independent research teams, the Supernova Cosmology Project led by Saul Perlmutter and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees, were studying type Ia supernova as standard candles to measure cosmic distances. These supernovae, resulting from the thermonuclear explosions of white dwarf stars, have a consistent peak luminosity, making them valuable tools for cosmic distance measurements. To the researchers' surprise, the data revealed that the expansion of the universe was not slowing down as expected due to gravity, but was instead accelerating. This discovery, which earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics, required the existence of a mysterious repulsive force that works against gravity on cosmic scales, dark energy. Observational evidence for dark energy has since accumulated from various sources. The cosmic microwave background, CMB, the afterglow of the Big Bang, provides crucial information about the geometry and content of the universe. Precise measurements of the CMB by missions such as WMAP and Planck have confirmed the presence of dark energy and helped constrain its properties. Large-scale structure surveys, which map the distribution of galaxies across vast cosmic distances, further support the dark energy paradigm by revealing how the clustering of matter has evolved over cosmic time. Current estimates suggest that dark energy constitutes about 68% of the energy density of the universe, with dark matter accounting for 27% and ordinary baryonic matter making up a mere 5%. This composition paints a picture of a universe dominated by components that are fundamentally mysterious to us, with the visible universe we can observe directly representing only a tiny fraction of the cosmic energy budget. The nature of dark energy remains one of the biggest open questions in physics. The simplest explanation, consistent with current observations, is the cosmological constant, a constant energy density filling space uniformly. This idea, originally introduced by Albert Einstein in his field equations of general relativity and later retracted as his biggest blunder, has been revived in the context of quantum field theory as vacuum energy. However, attempts to calculate the vacuum energy from first principles lead to values that are many orders of magnitude larger than observed, a discrepancy known as the cosmological constant problem. Alternative theories propose that dark energy is dynamic rather than constant. These models, often involving scalar fields similar to the Higgs field, allow for the possibility that the strength of dark energy changes over time. Quintessence models, for example, posit a scalar field whose energy density can vary in space and time. While current observations are consistent with a cosmological constant, future, more precise measurements may reveal subtle variations that could distinguish between different dark energy models. More radical proposals suggest that dark energy might not be a new component of the universe at all, but rather a manifestation of our incomplete understanding of gravity. Modified gravity theories, such as FR gravity or the Diwali-Gabadadze-Parati (DGP) model, attempt to explain the accelerating expansion by modifying Einstein's theory of general relativity on cosmic scales. While these theories face challenges in explaining all cosmological observations, they remain active areas of research. The quest to understand dark energy has spurred the development of ambitious observational programs. The Dark Energy Survey (DES), which concluded its observations in 2019, used the 4-meter Victor M. Blanco telescope in Chile to map hundreds of millions of galaxies, detect thousands of supernovae, and measure the clustering of matter over cosmic time. The survey's results have provided some of the most precise measurements of dark energy to date, constraining its equation of state parameter W to be consistent with 1, as predicted by the cosmological constant model. Looking to the future, several next-generation experiments promise to shed new light on the nature of dark energy. The Vera C. Rubin Observatory, set to begin operations in the mid-2020s, will conduct the Legacy Survey of Space and Time, LSST, imaging the entire visible southern sky every few nights. This unprecedented survey will provide a wealth of data on dark energy through multiple probes, including weak gravitational lensing, baryon acoustic oscillations, and the distribution of galaxies and clusters. Space-based missions will also play a crucial role in dark energy research. The European Space Agency's Euclid mission, launched in 2023, is designed to map the geometry of the dark universe by observing billions of galaxies out to 10 billion light-years. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will employ multiple techniques to study dark energy, including a wide-field infrared survey and a supernova survey to trace the expansion history of the universe with unprecedented precision. The implications of dark energy extend far beyond cosmology. If dark energy is indeed a cosmological constant, it implies a fundamental connection between quantum mechanics and general relativity, two pillars of modern physics that have resisted unification. Understanding dark energy could provide crucial insights into quantum gravity and potentially lead to a theory of everything that unifies all fundamental forces. Moreover, dark energy has profound implications for the ultimate fate of the universe. If dark energy continues to dominate, the universe will expand forever, eventually leading to a big freeze, where galaxies beyond our local group become unreachable and the night sky darkens as stars exhaust their fuel. Alternatively, if dark energy is dynamic, more exotic scenarios become possible, including a big rip, where even atoms are torn apart by the accelerating expansion. The study of dark energy also intersects with other areas of fundamental physics. The apparent fine-tuning of the cosmological constant has led some theorists to invoke the anthropic principle and the concept of a multiverse to explain its observed value. According to this view, our universe might be just one of countless universes with different physical constants, and we find ourselves in one compatible with the emergence of life. As research into dark energy continues, new experimental techniques and theoretical approaches are being developed. Gravitational wave astronomy, inaugurated by the detection of binary black hole mergers by LIGO, offers a new way to probe the expansion history of the universe through standard sirens. Future gravitational wave observatories, both on Earth and in space, could provide independent measurements of dark energy properties. The enigma of dark energy serves as a reminder of how much we have yet to learn about the fundamental nature of the universe. It challenges our most basic assumptions about physics and cosmology, driving innovation in theory, observation, and experimentation. As we continue to probe the mysteries of dark energy, we push the boundaries of human knowledge, seeking to understand the cosmic forces that shape the past, present, and future of our universe. The quest to unravel the nature of dark energy is emblematic of humanity's enduring curiosity about the cosmos. As we peer into the depths of space and time, searching for clues about this invisible force, we are reminded of the vastness and complexity of the universe. Yet, even as we grapple with these cosmic mysteries, our gaze is increasingly drawn back to our own celestial neighborhood. The exploration of our solar system, particularly the potential for human expansion beyond Earth, represents another frontier in our quest to understand and interact with the cosmos. Among the most tantalizing prospects for this expansion is the idea of space tourism, a concept that promises to bring the experience of spaceflight to a broader audience and potentially reshape our relationship with space exploration. Space tourism represents a revolutionary frontier in human spaceflight, promising to transform the once exclusive domain of government astronauts into an experience accessible to private citizens. This burgeoning industry aims to offer suborbital and orbital flights, stays on space stations, and potentially even lunar excursions to paying customers. As technological advancements and private sector investments converge, the dream of civilian space travel is rapidly transitioning from science fiction to reality. The concept of space tourism dates back to the early days of spaceflight, with Pan Am accepting reservations for future lunar flights in 1964. However, it wasn't until the turn of the 21st century that concrete steps toward realizing this vision began to materialize. The first space tourist, Dennis Tito, made history in 2001 when he paid a reported $20 million for an 8-day stay on the International Space Station, ISS, launched aboard a Russian Soyuz spacecraft. This milestone flight demonstrated the feasibility of private citizen spaceflight and sparked increased interest in the commercial potential of space tourism. Space tourism can be broadly categorized into several types of experiences. Suborbital flights, which reach the edge of space without completing a full orbit around Earth, offer a brief taste of weightlessness and a view of the planet's curvature. Orbital flights involve higher velocities and longer durations, allowing tourists to experience extended periods in microgravity and multiple orbits around Earth. More ambitious proposals include stays on commercial space stations and even trips around the Moon. The physics of space tourism involves overcoming Earth's gravity to reach space. For suborbital flights, vehicles must achieve a velocity of approximately 1 kilometer per second, 3,600 km/h, and reach an altitude of at least 100 kilometers, 62 miles, known as the Kármán line, the internationally recognized boundary of space. Orbital flights require much higher velocities of about 7.8 kilometers per second, 28,000 km/h, to achieve a stable orbit around Earth. Several private companies are at the forefront of developing space tourism capabilities. Virgin Galactic, founded by Richard Branson, has pioneered a unique air-launched spaceplane design. Their VSS Unity vehicle, carried to high altitude by a mothership before igniting its rocket engine, successfully completed its first fully crewed flight to the edge of space in July 2021. Blue Origin, founded by Amazon's Jeff Bezos, has developed the New Shepard, a more traditional vertical takeoff and landing rocket system for suborbital tourism. Blue Origin began commercial operations in July 2021, with Bezos himself participating in the inaugural crewed flight. For orbital tourism, SpaceX has taken a leading role. The company's Crew Dragon spacecraft, originally developed for NASA's Commercial Crew Program, completed the first all-civilian orbital mission, Inspiration, in September 2021. This three-day mission orbited Earth at an altitude higher than the ISS, demonstrating the potential for private orbital experiences beyond government space station visits. The development of space hotels represents the next frontier in space tourism. Several companies, including Axiom Space and Orbital Assembly Corporation, have announced plans for commercial space stations designed to accommodate tourists. Axiom Space aims to attach a commercial module to the ISS by 2024, eventually separating to form an independent commercial station. Orbital Assembly has proposed more ambitious designs for rotating stations that could provide artificial gravity, potentially mitigating some of the health effects of long-term microgravity exposure. Training and preparation for space tourists are crucial aspects of the industry. While early space tourists underwent months of intensive training similar to professional astronauts, companies are working to streamline this process for suborbital flights. Virgin Galactic's training program, for instance, lasts just a few days and focuses on safety procedures and maximizing the in-flight experience. Orbital missions, however, still require more extensive preparation due to the longer duration and more complex environment. The health and safety considerations for space tourism are significant. Suborbital flights expose passengers to high G-forces during launch and re-entry, as well as a brief period of microgravity. While these short exposures are generally well tolerated by healthy individuals, passengers must meet certain medical criteria. Orbital flights and extended stays in space present more complex challenges, including adaptation to microgravity, radiation exposure, and potential psychological effects of isolation and confinement. Environmental concerns surrounding space tourism have sparked debate within the scientific community and beyond. The carbon footprint of rocket launches, while currently small compared to other industries, could become significant if space tourism grows substantially. Additionally, the potential for space debris generation and the impact on Earth's upper atmosphere are areas of ongoing research and discussion. The legal and regulatory framework for space tourism is still evolving. In the United States, the Commercial Space Launch Amendments Act of 2004 provided a legal foundation for private spaceflight, establishing a framework for licensing and regulating commercial space vehicles. The FAA's Office of Commercial Space Transportation oversees these activities, balancing the need for safety with the desire to foster innovation in the industry. Internationally, the regulatory landscape is more complex, with ongoing discussions about how to apply existing space treaties to commercial activities. The economic potential of space tourism is substantial. A 2021 report by UBS estimated that space tourism could be a $3 billion market by 2030. This growth could have significant ripple effects, driving innovation in aerospace technology, creating new job opportunities, and potentially lowering the cost of access to space for scientific and commercial applications. The cultural impact of space tourism extends beyond economics. The overview effect, a cognitive shift reported by many astronauts upon seeing Earth from space, could become accessible to a wider range of people, potentially influencing public perception of global issues like climate change. Furthermore, the democratization of space access could inspire a new generation of scientists, engineers, and entrepreneurs to pursue careers in space-related fields. As space tourism evolves, several challenges and opportunities lie ahead. Reducing costs to make space travel accessible to a broader segment of the population remains a primary goal. Technological advancements in reusable rocket systems, like those developed by SpaceX and Blue Origin, are crucial steps in this direction. Improving safety and reliability will also be paramount as the industry scales up operations. The future of space tourism may extend beyond Earth orbit. NASA's Artemis program, aimed at returning humans to the Moon, has opened the door for potential commercial lunar activities. Companies like SpaceX and Blue Origin are developing vehicles capable of lunar landings, which could eventually be adapted for tourism purposes. Even more ambitiously, Mars has been proposed as a long-term destination for space tourism, though such missions remain in the realm of speculation for now. Space tourism represents a paradigm shift in humanity's relationship with space. By making spaceflight accessible to private citizens, it has the potential to accelerate technological development, inspire scientific pursuits, and reshape our perspective on Earth and our place in the universe. As the industry continues to evolve, it will likely play a crucial role in the broader context of space exploration and utilization, contributing to humanity's expansion into the final frontier. As we contemplate the exciting possibilities of space tourism and its potential to bring the experience of spaceflight to a broader audience, we are reminded of the vast and largely unexplored frontiers that lie beyond our planet. While space tourism focuses on bringing humans to space, another equally fascinating aspect of space exploration involves the search for life beyond Earth. This quest, which combines cutting-edge technology with some of humanity's most profound questions about our place in the universe, takes us from the familiar confines of our solar system to the distant reaches of the galaxy in the search for extraterrestrial intelligence. The quest to find intelligent life beyond Earth represents one of humanity's most profound and enduring scientific endeavors. This multidisciplinary field, known as the search for extraterrestrial intelligence, SETI, combines astronomy, biology, and technology in an attempt to answer the age-old question, are we alone in the universe? SETI efforts span from scanning the cosmos for artificial radio signals to searching for signs of advanced civilizations through their potential technological signatures. The modern era of SETI began in 1959 with the seminal paper by physicists Giuseppe Cocconi and Philip Morrison, who proposed using microwave radio to communicate between the stars. This idea was quickly put into practice by Frank Drake, who conducted the first modern SETI experiment, Project Ozma, in 1960. Using a 26-meter radio telescope, Drake targeted two nearby sun-like stars, Tau Ceti and Epsilon Eridani, listening for any signs of intelligent transmissions. Although no signals were detected, Project Ozma set the stage for future SETI efforts and sparked scientific interest in the possibility of detecting extraterrestrial intelligence. The scientific principles underlying SETI are rooted in our understanding of physics and astronomy. Radio CT, the most common form of search, relies on the fact that radio waves can travel vast distances through space with relatively little attenuation. Certain frequencies, particularly those around 1.420 GHz, the emission frequency of neutral hydrogen, are thought to be natural choices for interstellar communication due to their ability to penetrate interstellar dust and gas. Optical SETI, a more recent development, searches for brief, powerful laser pulses that an advanced civilization might use for communication or as a byproduct of their technology. One of the most significant challenges in SETI is the vast scale of the search. The Milky Way galaxy alone contains an estimated 400 billion stars, and current estimates suggest there may be more planets than stars. The sheer number of potential targets necessitates both patience and the development of increasingly sophisticated search techniques. The Drake equation, formulated by Frank Drake in 1961, attempts to estimate the number of detectable civilizations in our galaxy. While the equation's parameters are highly uncertain, it serves as a valuable framework for discussing the factors influencing the prevalence of intelligent life in the universe. Technological ambitious SETI projects to date is Breakthrough Listen, launched in 2015 with a $100 million budget. This initiative uses some of the world's most powerful telescopes to survey the million closest stars to Earth, the entire galactic plane, and 100 nearby galaxies. The project not only listens for radio signals, but also searches for optical laser transmissions, casting a wide net in the search for extraterrestrial intelligence. While SETI has traditionally focused on detecting communication signals, the field has expanded to include the search for technosignatures, observable signs of technology that might indicate the presence of an advanced civilization. These could include megastructures like Dyson spheres, hypothetical structures that encompass a star to capture its energy output, atmospheric pollutants that might indicate industrial activity, or even the heat signatures of advanced civilizations. The search for technosignatures broadens the scope of SETI, allowing for the possibility of detecting civilizations that may not be actively trying to communicate. The Fermi paradox, named after physicist Enrico Fermi, poses a challenging question to SETI researchers. If intelligent life is common in the universe, why haven't we detected it yet? Numerous explanations have been proposed, ranging from the idea that advanced civilizations are rare or short-lived, to the possibility that they choose not to communicate or expand beyond their home systems. The Great Filter hypothesis suggests that there might be a developmental stage that is extremely difficult for civilizations to pass through, explaining the apparent lack of detectable alien life. Interstellar messages have been another aspect of SETI efforts. The Arecibo message, transmitted in 1974 towards the globular star cluster M13, was one of the first deliberate attempts to communicate with extraterrestrial intelligence. More recently, the Breakthrough Message competition sought to create digital messages representing humanity and Earth that could potentially be transmitted to other civilizations. These efforts raise complex ethical and philosophical questions about the wisdom of actively broadcasting our presence to the cosmos. The discovery of thousands of exoplanets in recent years has had a profound impact on SETI. The realization that planets are common around other stars has bolstered the case for the potential ubiquity of life in the universe. Missions like NASA's Transiting Exoplanet Survey satellite, TESS, continue to expand our catalogue of nearby exoplanets, providing SETI researchers with promising targets for their searches. The characterization of exoplanet atmospheres, a capability that will be greatly enhanced by the James Webb Space Telescope, may allow for the detection of biosignatures, chemical signs of life, on distant worlds. The implications of a successful SETI detection would be profound, potentially representing one of the most significant discoveries in human history. It would provide definitive proof that we are not alone in the universe and could offer insights into the development and longevity of technological civilizations. The nature of the detected signal or technosignature could provide clues about the level of technological advancement of the civilization and potentially even information about their society and culture. Protocols have been developed for how to respond in the event of a potential SETI detection. The International Academy of Astronautics SETI Permanent Committee has established a set of post-detection protocols that emphasize the importance of verification, public disclosure, and international consultation before any response is made. These protocols reflect the understanding that contact with an extraterrestrial civilization would be an event of global significance. requiring careful consideration and coordination. Despite decades of searching, SETI has yet to detect any confirmed signs of extraterrestrial intelligence. However, this lack of detection does not necessarily imply that we are alone in the universe. Given the vast scales of space and time involved and our limited search capabilities to date, the current null results are consistent with a wide range of possibilities for the prevalence of intelligent life in the cosmos. As SETI moves forward, new technologies and approaches continue to expand the scope and sensitivity of the search. The development of next-generation radio telescopes, like the Square Kilometre Array (SKA), promises to dramatically increase our ability to detect faint signals from distant stars. Advances in exoplanet detection and characterization techniques may allow for more targeted searches of potentially habitable worlds. The integration of machine learning and artificial intelligence is likely to play an increasingly important role in analyzing the vast amounts of data generated by SETI observations. The search for extraterrestrial intelligence stands at the intersection of science, technology, and philosophy. It challenges us to consider our place in the cosmos and the potential paths that intelligent life might take as it evolves and expands into the universe. Whether or not SETI ultimately succeeds in detecting signs of extraterrestrial intelligence, the search itself drives technological innovation, sparks scientific inquiry, and encourages us to contemplate some of the most fundamental questions about our existence and the nature of intelligence in the universe. As we continue to scan the skies for signs of intelligent life, we are reminded of the vast scales and complexities involved in space exploration. The search for extraterrestrial intelligence pushes the boundaries of our technological capabilities, requiring us to develop ever more sensitive instruments and sophisticated data analysis techniques. This drive for technological advancement in the pursuit of cosmic understanding is mirrored in other areas of space exploration, including the development of advanced propulsion systems. As we look beyond our solar system in search of other civilizations, we must also consider how we might one day reach the stars ourselves, bringing us to the cutting-edge field of interstellar propulsion and the challenge of breaking free from the limitations of conventional rocket technology. As humanity ventures further into the cosmos, the need for precise navigation becomes increasingly critical. Quantum navigation in deep space represents a cutting-edge approach to solving the complex challenges of interstellar travel and exploration. This technology, rooted in the principles of quantum mechanics, promises to revolutionize our ability to determine position, velocity, and time with unprecedented accuracy in the vast expanse of space. The foundation of quantum navigation lies in the unique properties of quantum systems, particularly the phenomenon of quantum entanglement. Entanglement occurs when two or more particles become correlated in such a way that the quantum state of each particle cannot be described independently, even when separated by large distances. This spooky action at a distance, as Einstein famously described it, forms the basis for many quantum technologies, including navigation systems. One of the key components of quantum navigation is the quantum clock, an ultra-precise timekeeping device that utilizes the quantum properties of atoms or ions. These clocks, such as optical lattice clocks or single-ion clocks, can achieve accuracies on the order of 10 or 18, losing or gaining less than a second over the entire age of the universe. This level of precision is crucial for deep space navigation, where even tiny errors in timekeeping can lead to significant positional uncertainties over vast distances. The principles of quantum navigation build upon traditional space navigation techniques while offering significant improvements. Conventional deep space navigation often relies on a combination of inertial measurements and periodic updates from Earth-based tracking stations. However, as spacecraft venture farther from Earth, the time delay in communications increases and the accuracy of Earth-based tracking decreases. Quantum navigation systems aim to provide autonomous navigation capabilities that maintain high accuracy over extended periods without external updates. One promising approach to quantum navigation involves the use of quantum sensors to measure gravitational fields. These sensors, based on atom interferometry, can detect minute variations in the gravitational pull of celestial bodies. By mapping these gravitational fields with extreme precision, A spacecraft could determine its position relative to known astronomical objects, effectively creating a gravitational map for navigation. This technique could be particularly valuable in regions of space where traditional navigation methods, such as using pulsars as beacons, may be less effective. Another aspect of quantum navigation is the development of quantum gyroscopes. These devices use the quantum properties of atoms or photons to measure rotation with exquisite sensitivity. Unlike traditional gyroscopes, which can drift over time, quantum gyroscopes promise long-term stability and accuracy. This is crucial for maintaining spacecraft orientation during long-duration missions, where even small errors can compound over time to significant deviations in trajectory. The potential applications of quantum navigation extend beyond mere positional accuracy. Quantum communication systems, based on the principles of quantum key distribution, could provide secure and instantaneous communication across vast distances. This technology relies on the quantum no-cloning theorem, which states that it is impossible to create an identical copy of an unknown quantum state. Any attempt to intercept or measure the quantum information would inevitably disturb the system, alerting the communicating parties to the presence of an eavesdropper. The development of quantum navigation systems for deep space exploration faces several significant challenges. One of the primary hurdles is the need to miniaturize and ruggedize quantum technologies for space applications. Many quantum devices currently require precisely controlled laboratory conditions to function, including ultra-low temperatures and minimal vibration, adapting these sensitive systems to withstand the harsh environment of space, including radiation exposure and extreme temperature fluctuations, requires significant engineering innovation. Despite these challenges, progress in quantum navigation for space applications has been steady. NASA's Cold Atom Laboratory, launched to the International Space Station in 2018, has demonstrated the ability to create Bose-Einstein condensates in microgravity, a crucial step towards developing space-based quantum sensors. Meanwhile, the European Space Agency, ESA, has proposed the Space Optical Clock, SOC, mission, which aims to place an optical lattice clock in orbit to test fundamental physics and advance space-based timekeeping. The implications of quantum navigation for deep space exploration are profound. With the ability to navigate autonomously and with unprecedented accuracy, future spacecraft could venture into the outer reaches of the solar system and beyond with greater confidence. This technology could enable more precise planetary landings, facilitate complex maneuvers in multi-body gravitational fields, and support long-duration missions to distant stars. Moreover, the development of quantum navigation systems has potential benefits beyond space exploration. The ultra-precise timekeeping and sensing capabilities could find applications in Earth-based technologies, from improved GPS systems to more accurate gravitational field mapping for geophysical studies. The advances in quantum communication could revolutionize secure data transmission, with implications for fields ranging from finance to national security. As research in quantum navigation progresses, several areas remain ripe for future investigation. The integration of quantum navigation with artificial intelligence and machine learning algorithms could lead to adaptive navigation systems capable of optimizing trajectories in real time based on quantum sensor data. Additionally, the exploration of more exotic quantum phenomena, such as quantum radar or quantum imaging, could further enhance our ability to map and navigate through deep space. The ethical implications of quantum navigation technology also warrant consideration. As these systems become more advanced, questions arise about the potential militarization of space and the need for international agreements governing the use of ultra-precise navigation capabilities in both terrestrial and space-based applications. In conclusion, quantum navigation in deep space represents a convergence of cutting-edge physics, advanced engineering, and space exploration ambitions. By harnessing the strange and powerful properties of quantum mechanics, we stand on the brink of a new era in space travel, one where the vast distances between stars may become more manageable and the mysteries of the cosmos more accessible. As we continue to refine and develop these technologies, we move closer to realizing the dream of becoming a truly spacefaring civilization, capable of navigating the cosmic ocean with unprecedented precision and confidence. As we contemplate the incredible potential of quantum navigation to guide us through the depths of space, we are reminded of the vast scales and complexities involved in space exploration. The ability to navigate with quantum precision opens up new possibilities for long-duration missions and interstellar travel. However, as we look to the stars, we must also consider the tools we use to observe and understand them. This brings us to another frontier in space technology, the development of next-generation space telescopes, which promise to extend our vision far beyond what is currently possible, potentially revealing new worlds and unraveling cosmic mysteries that have long eluded us. The exploration of the cosmos has been revolutionized by space-based telescopes, instruments that orbit above Earth's atmosphere to provide unparalleled views of the universe. As we look to the future, the next generation of space telescopes promises to push the boundaries of our understanding even further, offering unprecedented insights into the nature of dark matter, the formation of the first galaxies, and the potential for life on exoplanets. These advanced observatories will build upon the legacy of their predecessors, incorporating cutting-edge technologies to overcome current limitations and open new frontiers in astronomy and astrophysics. The history of space telescopes dates back to 1990 with the launch of the Hubble Space Telescope, HST, which has since provided iconic images and groundbreaking scientific discoveries that have transformed our view of the universe. Hubble's success paved the way for subsequent missions like the Spitzer Space Telescope, the Chandra X-ray Observatory, and most recently, the James Webb Space Telescope, JWST, launched in December 2021. Each of these observatories has expanded our capabilities in different wavelengths of the electromagnetic spectrum, from the ultraviolet and visible light of Hubble to the infrared sensitivity of JWST. The next generation of space telescopes will build upon these achievements, incorporating advancements in optics, detector technology, and spacecraft design. One of the most ambitious concepts is for telescopes with significantly larger primary mirrors than current observatories. While JWST boasts a 6.5-meter primary mirror, future telescopes could feature mirrors 15 meters or larger in diameter. These larger apertures would allow for greater light-gathering capability and improved resolution, enabling astronomers to observe fainter and more distant objects with unprecedented clarity. The technical challenges of constructing and launching such large telescopes are formidable. Traditional monolithic mirrors become impractical beyond certain sizes due to weight constraints and the limited payload capacity of launch vehicles. To overcome this, engineers are developing advanced segmented mirror technologies and lightweight materials. For instance, the proposed large ultraviolet optical infrared surveyor LUVOIR concept envisions a primary mirror composed of multiple segments that unfold and align precisely in space, similar to JWST but on an even grander scale. Another revolutionary concept in space telescope design is the use of formation flying technology to create a virtual telescope of enormous proportions. This approach, known as interferometry, involves multiple spacecraft working in concert to act as a single, much larger instrument. The proposed Laser Interferometer Space Antenna, LISA mission, while designed to detect gravitational waves rather than electromagnetic radiation, demonstrates the potential of this technology. Future optical interferometers in space could achieve effective apertures of hundreds or even thousands of kilometers, providing resolution far beyond what is possible with a single telescope. Advancements in detector technology will also play a crucial role in the capabilities of future space telescopes. The development of larger, more sensitive detector arrays will allow for wider fields of view and the ability to gather more data in shorter observation times. Superconducting detectors, operating at temperatures near absolute zero, promise to push the boundaries of sensitivity, potentially allowing for the direct imaging of Earth-like exoplanets around nearby stars. One of the primary scientific goals driving the development of next-generation space telescopes is the characterization of exoplanet atmospheres. While current telescopes like JWST can study the atmospheres of some gas giant exoplanets, Future observatories aim to analyze the composition of Earth-sized planets in the habitable zones of their stars. This capability could potentially detect biosignatures, chemical markers that might indicate the presence of life, in the atmospheres of these distant worlds. The proposed HABEX, Habitable Exoplanet Observatory concept, for example, includes a coronagraph and star shade to block out the light of host stars, allowing for direct observation of orbiting planets. The study of the early universe is another key area where future space telescopes will make significant contributions. By observing in multiple wavelengths with unprecedented sensitivity, these instruments will be able to peer back to the era of the first stars and galaxies, shedding light on how the universe evolved from the cosmic dark ages to the rich tapestry of galaxies we see today. The ability to observe the universe at different epochs will provide crucial data for testing and refining cosmological models, potentially resolving outstanding questions about the nature of dark matter and dark energy. The development of next-generation space telescopes faces several technological hurdles. Maintaining the precise alignment and stability required for these advanced optical systems in the harsh environment of space presents significant engineering challenges. Innovative solutions, such as advanced thermal management systems and ultra-stable structures, are being developed to address these issues. Additionally, the vast amounts of data generated by these observatories will require new approaches to data processing and analysis, likely incorporating machine learning and artificial intelligence techniques to sift through the wealth of information and identify key findings. The potential for serendipitous discoveries with these advanced telescopes cannot be overstated. Just as Hubble's deep field observations revealed an unexpected abundance of distant galaxies, future telescopes may uncover phenomena that are currently unknown or merely theoretical. The improved sensitivity and resolution could reveal new classes of astronomical objects, unexpected interactions between known phenomena, or even hints of exotic physics beyond our current understanding. International collaboration will likely play a crucial role in the development and operation of next-generation space telescopes. The scale and complexity of these projects often exceed the resources of any single nation, necessitating partnerships between space agencies, academic institutions, and private industry. Such collaborations not only pool financial and technical resources, but also bring together diverse expertise and perspectives, potentially leading to more innovative and comprehensive mission designs. The implications of these advanced space telescopes extend far beyond the realm of professional astronomy. The images and discoveries from these observatories have the potential to captivate the public imagination, fostering interest in science and space exploration. Educational outreach programs associated with these missions could inspire the next generation of scientists and engineers, while the technological spin-offs from telescope development could find applications in fields ranging from medicine to environmental monitoring. As we look to the future of space telescopes, we stand on the threshold of a new era in our exploration of the cosmos. These advanced observatories promise to reveal the universe in unprecedented detail, from the atmospheres of distant exoplanets to the first moments after the Big Bang. They represent not just technological marvels but gateways to new understanding, challenging our theories and expanding our cosmic perspective. The development of next-generation space telescopes embodies humanity's enduring quest to understand our place in the universe. As these instruments peer ever deeper into space and time, they not only advance our scientific knowledge, but also spark philosophical contemplation about our origins and potential futures. Each new discovery has the potential to reshape our understanding of the cosmos and our place within it, driving us to explore further and dream bigger. As we anticipate the groundbreaking observations that future space telescopes will provide, we are reminded of the intricate dance between technological advancement and scientific discovery. The ability to see farther and more clearly into the cosmos inevitably raises new questions and challenges. One such challenge, growing increasingly urgent as our presence in space expands, is the issue of space debris. The very orbital paths that provide ideal vantage points for our telescopes are becoming cluttered with the remnants of past missions, threatening not only our observational capabilities, but also the future of space exploration itself. This pressing concern brings us to consider the critical task of managing and mitigating space debris to ensure the continued viability of our endeavors beyond Earth's atmosphere. As humanity stretches its reach beyond Earth, the challenge of sustaining life in the harsh environment of space becomes paramount. Space agriculture, the cultivation of plants in extraterrestrial environments, stands at the forefront of this challenge, offering solutions for long-duration space missions and potential off-world colonies. This field encompasses a wide range of disciplines, from botany and genetics to environmental engineering and materials science, all working in concert to create sustainable food production systems beyond our home planet. The concept of growing plants in space is not new, with experiments dating back to the early days of space exploration. However, recent advancements in technology and our understanding of plant biology have brought space agriculture closer to practical reality. The primary goal of space agriculture is to provide a sustainable source of food, oxygen, and psychological well-being for astronauts on extended missions or future colonists on other celestial bodies. One of the key challenges in space agriculture is the development of efficient hydroponic and aeroponic systems that can function in microgravity or low-gravity environments. Hydroponics, which involves growing plants in nutrient-rich water without soil, has been successfully demonstrated on the International Space Station, ISS, through experiments like NASA's Veggie project. This system uses LED lights and a special growth medium to cultivate small crops of lettuce and other vegetables. Aeroponics, a more advanced technique where plant roots are suspended in air and misted with nutrient solution, offers even greater water efficiency and potential for larger-scale production in space environments. The effects of microgravity on plant growth present both challenges and opportunities for space agriculture. While plants can grow in the absence of gravity, they exhibit altered growth patterns and physiological responses. For example, roots may grow in random directions rather than downward, and fluid distribution within plant tissues can be affected. Understanding and mitigating these effects is crucial for developing successful space agriculture systems. Research on the ISS has shown that certain plant species are more adaptable to microgravity conditions, leading to efforts to identify and develop space-hardy crop varieties. Genetic engineering plays a significant role in adapting plants for space environments. Scientists are working to develop crops that are more resistant to radiation, require less water and nutrients, and have improved nutritional profiles. The CRISPR-Cas9 gene editing technique has opened new avenues for creating plants tailored to the unique challenges of space cultivation. For instance, researchers are exploring ways to enhance plants' ability to recycle oxygen and remove excess carbon dioxide, which could be crucial for maintaining breathable atmospheres in enclosed space habitats. Lighting is another critical factor in space agriculture. In the absence of natural sunlight, artificial lighting systems must be optimized for plant growth while minimizing energy consumption. Advanced LED systems that can be tuned to specific wavelengths most efficient for photosynthesis are being developed and tested. These systems not only provide the necessary light for plant growth, but also offer the potential to manipulate plant characteristics, such as flavor profiles and nutrient content, by adjusting light spectra. Nutrient cycling and waste management are integral components of sustainable space agriculture systems. In the closed environment of a spacecraft or space habitat, efficient recycling of nutrients is essential. Bioregenerative life support systems, which aim to mimic Earth's natural cycles, are being developed to integrate plant cultivation with waste processing. For example, the Melissa Microecological Life Support System Alternative project, led by the European Space Agency, is working on a closed-loop system that uses microorganisms to break down organic waste and convert it into nutrients for plant growth. Water management in space agriculture presents unique challenges and opportunities. In microgravity, water behaves differently, forming spheres that can float away rather than flowing as it does on Earth. Developing systems to efficiently deliver water to plant roots while preventing water loss through evaporation is crucial. Some innovative solutions include using hydrogels or other water-retaining materials in growth mediums and developing precision irrigation systems that deliver water directly to plant roots. The psychological benefits of space agriculture should not be underestimated. Studies have shown that interacting with plants can reduce stress and improve mood, which is particularly important for astronauts on long-duration missions. The presence of growing plants in space habitats can provide a connection to Earth and a sense of purpose beyond the immediate mission objectives. Furthermore, the act of cultivating plants can offer a therapeutic and engaging activity for crew members during extended periods in isolated and confined environments. Recent missions have demonstrated significant progress in space agriculture. The Advanced Plant Habitat on the ISS, a fully automated growth chamber, has successfully grown several generations of plants, providing valuable data on plant life cycles in space. The Chinese Chang'e 4 mission to the far side of the Moon included a biological experiment that successfully sprouted cotton seeds, marking the first time a plant had germinated on another world. Looking to the future, space agriculture will play a crucial role in plans for lunar bases and Mars colonization. NASA's Artemis program, which aims to establish a sustainable human presence on the Moon, includes plans for developing lunar greenhouses. These facilities will serve as testbeds for technologies and techniques that could later be applied to Martian colonies. The challenges of growing plants on Mars, with its thin atmosphere, extreme temperature fluctuations, and high radiation levels, are formidable but not insurmountable. Concepts for Martian greenhouses include using local regolith as a growth medium and extracting water from the Martian soil or atmosphere. The development of space agriculture technologies has implications that extend far beyond space exploration. Many of the innovations in water and resource efficiency, controlled environment agriculture, and plant genetics have direct applications on Earth. These technologies could help address food security issues in arid regions, improve urban farming techniques, and contribute to more sustainable agricultural practices globally. As we continue to advance our capabilities in space agriculture, several key areas require further research and development. Improving the nutritional density and variety of space-grown crops, developing more robust and self-sustaining ecosystems, and scaling up production to support larger crews or colonies are all critical challenges. Additionally, the long-term effects of space radiation on plant genetics and food safety need to be thoroughly understood and mitigated. The field of space agriculture represents a convergence of human ingenuity, scientific knowledge, and technological innovation. It embodies our species, adaptability, and determination to thrive in even the most challenging environments. As we cultivate crops in the cosmos, we are not just growing food, we are nurturing the seeds of human expansion into the solar system and beyond. The success of space agriculture will be a crucial factor in determining the feasibility and sustainability of long-term human presence beyond Earth. As we contemplate the green shoots of plants growing in the sterile environment of spacecraft and future space colonies, we are reminded of the delicate balance of life and the ingenuity required to sustain it beyond our home planet. The ability to grow food in space is a critical step towards long-term space exploration and colonization. However, as we look to the stars with dreams of cultivating new worlds, we must also consider the health and well-being of the humans who will undertake these ambitious journeys. This brings us to another crucial aspect of space exploration, the field of space medicine, which addresses the unique medical challenges posed by extended periods in the alien environment of space. The exploration and utilization of space have led to remarkable scientific discoveries and technological advancements that benefit humanity. However, these activities have also resulted in an unintended consequence: the accumulation of space debris in Earth's orbit. This growing cloud of man-made objects, ranging from defunct satellites to tiny fragments of paint, poses a significant threat to active satellites, spacecraft, and future space missions. The challenge of managing and mitigating space debris has become a critical concern for the global space community, demanding innovative solutions to ensure the sustainable use of Earth's orbital environment. Space debris, also known as orbital debris or space junk, encompasses all artificial objects orbiting Earth that no longer serve a useful purpose. This includes spent rocket stages, non-functional satellites, fragments from collisions or explosions, and even small particles like paint flakes or solidified coolant droplets. The size of these objects varies greatly, from microscopic particles to large structures several meters across. As of 2024, it is estimated that there are over 34,000 objects larger than 10 centimeters in orbit, approximately 900,000 objects between 1 centimeters and 10 centimeters, and millions of particles smaller than 1 centimeter. The problem of space debris began with the launch of the first artificial satellite, or Sputnik 1, in 1957. Since then, the number of objects in orbit has grown exponentially due to increased space activities, satellite deployments, and fragmentation events. A significant contributor to the current debris population was the Chinese anti-satellite missile test in 2007, which destroyed the Fengyun 1C weather satellite and created over 3,000 trackable fragments. Another major event was the accidental collision between the active Iridium-33 and the defunct Cosmos 2251 satellites in 2009, which generated more than 2,000 trackable pieces of debris. The dangers posed by space debris are multifaceted. Even small particles traveling at orbital velocities, typically around 7 to 8 km/s, can cause significant damage to spacecraft due to their high kinetic energy. A 1 cm aluminum sphere at these speeds carries the same kinetic energy as a car traveling at 80 km/h. Larger objects pose catastrophic risks, potentially destroying satellites or creating new debris fields through collisions. The International Space Station, ISS, regularly performs debris avoidance maneuvers to protect its crew and structure from potential impacts. The Kessler syndrome, proposed by NASA scientist Donald J. Kessler in 1978, describes a scenario where the density of objects in low Earth orbit becomes high enough that collisions between objects could cause a cascade effect. Each collision would generate more debris, increasing the likelihood of further collisions and potentially rendering certain orbital ranges unusable for generations. This theoretical scenario underscores the urgency of addressing the space debris problem before it becomes self-sustaining. Efforts to map and track space debris have intensified in recent years. The U.S. Space Surveillance Network uses a combination of ground-based radar and optical telescopes to maintain a catalogue of trackable objects in orbit. Similarly, the European Space Agency, ESA, operates its Space Debris Office, which conducts research and provides services related to space debris. These tracking efforts are crucial for collision avoidance and for understanding the evolving debris environment. Mitigating the growth of space debris involves both preventive measures and active debris removal. Preventive measures include designing satellites for end-of-life disposal, either through controlled re-entry into Earth's atmosphere or by moving them to graveyard orbits above active satellite constellations. International guidelines, such as those developed by the Interagency Space Debris Coordination Committee, IADC, recommend that satellites in low Earth orbit should be deorbited within 25 years of mission completion. Active debris removal, ADR technologies, are being developed to tackle the existing debris population. These range from concepts like space nets and harpoons to capture large debris objects, to laser systems that could nudge smaller debris into lower orbits where they would eventually burn up in the atmosphere. The Remove Debris mission, led by the University of Surrey and funded in part by the European Commission, successfully demonstrated several ADR technologies in orbit, including a net capture system and a vision-based navigation system for rendezvous with debris objects. Another promising approach is the use of electrodynamic tethers for debris removal. These long, conductive tethers interact with Earth's magnetic field to generate drag, gradually lowering the orbit of attached debris. The Japanese space agency JAXA has been experimenting with this technology, although technical challenges remain in deploying and controlling such tethers in the space environment. The economic implications of space debris are significant. The global satellite industry, valued at hundreds of billions of dollars, relies on a stable and safe orbital environment. The cost of shielding spacecraft against debris impacts, performing collision avoidance maneuvers, and potentially replacing damaged or destroyed satellites adds substantial financial burden to space operations. Moreover, the risk of debris collisions could deter future investments in space infrastructure and exploration. Legal and policy frameworks play a crucial role in addressing the space debris issue. The Outer Space Treaty of 1967, while not specifically addressing debris, establishes principles of responsibility for space activities. More recent efforts, such as the UN Space Debris Mitigation Guidelines and national regulations, aim to reduce the creation of new debris. However, the challenge of enforcing these guidelines and the lack of binding international agreements on debris removal remain significant hurdles. Emerging technologies offer new possibilities for debris mitigation. Advances in materials science could lead to spacecraft designs that are more resistant to debris impacts or that minimize fragmentation in case of collision. Small, maneuverable janitor satellites could be deployed to collect debris or shepherd it into safer orbits. Some researchers are even exploring the possibility of using ground-based lasers to alter the orbits of small debris particles, nudging them towards re-entry. The future of space debris management will likely involve a combination of technological, legal, and economic solutions. Improved tracking capabilities, including the use of artificial intelligence to predict collision risks, will be crucial. International cooperation will be essential, as the problem of space debris affects all spacefaring nations and requires a coordinated global response. As we continue to explore and utilize space, the management of orbital debris will remain a critical challenge. The solutions developed to address this issue not only ensure the continued viability of space operations, but also reflect our capacity to act as responsible stewards of the near-Earth space environment. The efforts to clean up Earth's orbital space serve as a reminder of the need for sustainable practices in all aspects of space exploration and utilization. The challenge of space debris underscores the interconnectedness of Earth and space environments, highlighting how human activities in orbit can have long-lasting consequences. As we work to ensure the safety and sustainability of our orbital infrastructure, we are also developing technologies and practices that could be applied to future exploration and colonization efforts beyond Earth. This brings us to consider the next frontier in space. Space medicine encompasses the study of the physiological and psychological effects of spaceflight on the human body, as well as the development of countermeasures to mitigate these effects. This specialized branch of medicine addresses unique challenges posed by the space environment, including microgravity, radiation exposure, and isolation, which can have profound impacts on human physiology and psychology. The effects of microgravity on the human body have been a primary focus of space medicine since the early days of human spaceflight. In the absence of Earth's gravitational pull, the body undergoes significant changes across multiple physiological systems. One of the most notable effects is bone loss, with astronauts losing an average of 1 to 1.5% of bone mass per month in space. This loss occurs primarily in weight-bearing bones and is caused by the reduced mechanical stress on the skeletal system in microgravity. To combat this, astronauts on the International Space Station, ISS, engage in rigorous exercise routines using specialized equipment designed for use in microgravity, such as the Advanced Resistive Exercise Device, ARED. Muscle atrophy is another significant concern in microgravity environments. Without the constant work of counteracting gravity, muscles begin to weaken and shrink. Studies have shown that astronauts can lose up to 20% of their muscle mass on space flights lasting 5 to 11 days. This muscle loss not only affects strength, but also impacts the body's metabolism and overall health. Countermeasures include resistance exercises and the use of vibration platforms to stimulate muscle activity. The cardiovascular system also undergoes significant changes in space. In microgravity, fluids in the body shift towards the upper body and head, a phenomenon known as fluid shift. This can lead to facial swelling, congestion, and increased intracranial pressure. Over time, the heart adapts to the reduced workload by decreasing in size, which can lead to cardiovascular deconditioning. Upon return to Earth, astronauts may experience orthostatic intolerance, a condition where blood pressure drops abnormally when standing up, leading to dizziness and fainting. Space radiation presents another major challenge for long-duration spaceflight. Beyond the protection of Earth's magnetosphere, astronauts are exposed to higher levels of ionizing radiation, including galactic cosmic rays and solar particle events. This increased radiation exposure can lead to a higher risk of cancer, cataracts, and potential cognitive impairment. Shielding spacecraft and habitats is one approach to mitigating radiation exposure, but the mass requirements for effective shielding pose significant challenges for long-distance space travel. Researchers are exploring innovative solutions, including the use of water as a radiation shield and the development of biomedical countermeasures to enhance the body's natural radiation resistance. The space environment also affects the sensory systems, particularly vision. Many astronauts experience vision changes during long-duration space flights, a condition known as spaceflight-associated neuroocular syndrome, SANS. This syndrome can include optic disc edema, globe flattening, and hyperopic shifts, potentially leading to long-term vision problems. The exact mechanisms behind SANS are still being studied, but it is thought to be related to the fluid shifts and increased intracranial pressure experienced in microgravity. The immune system is another area of concern in space medicine. Studies have shown that spaceflight can lead to immune dysregulation, with some aspects of the immune system becoming suppressed while others are overactivated. This altered immune function can increase susceptibility to infections and potentially reactivate latent viruses. Researchers are investigating ways to boost immune function in space, including nutritional supplements and targeted exercise programs. Psychological health is a critical component of space medicine, particularly for long-duration missions. The isolation, confinement, and extreme environment of space can lead to stress, anxiety, and interpersonal conflicts among crew members. Studies on Earth, such as the Mars 500 experiment, which simulated a 520-day mission to Mars, have provided valuable insights into the psychological challenges of long-term space missions. Strategies to maintain psychological well-being include regular communication with family and friends on Earth, carefully designed living and working spaces, and the use of virtual reality technology to provide sensory variety and connection to Earth. Sleep disturbances are common in space, with the lack of normal day-night cycles and the noise of spacecraft systems contributing to disrupted sleep patterns. Poor sleep can affect cognitive performance, mood, and overall health. Lighting systems that mimic Earth's day-night cycle and carefully scheduled sleep periods are used to help maintain circadian rhythms in space. The development of medical technologies for use in space presents unique challenges. Medical equipment must be compact, lightweight, and able to function in microgravity. Advances in telemedicine have been crucial for space medicine, allowing Earth-based doctors to diagnose and treat astronauts remotely. Future long-duration missions, such as those to Mars, will require even greater medical autonomy, potentially including surgical capabilities and advanced diagnostic tools. Pharmacology in space is another area of ongoing research. The absorption, distribution, and effectiveness of medications can be altered in the space environment. Additionally, the shelf life of drugs may be affected by the increased radiation exposure. Researchers are working on developing stable, long-lasting medications and exploring new drug delivery systems suitable for use in space. The study of space medicine has implications that extend far beyond space exploration. Many of the technologies and treatments developed for space have found applications in terrestrial medicine. For example, research on bone loss in space has led to improved treatments for osteoporosis on Earth. Similarly, advances in telemedicine driven by the needs of space missions have benefited remote and underserved communities on our planet. As we look towards future missions to the Moon, Mars, and beyond, space medicine will play a crucial role in enabling long-term human presence in space. The challenges of maintaining human health during years-long missions to other planets are formidable, but not insurmountable. Ongoing research on the ISS and in ground-based analogues continues to provide valuable data on the long-term effects of spaceflight on the human body. The field of space medicine embodies the interdisciplinary nature of space exploration, bringing together experts from diverse fields including medicine, biology, physics, and engineering. As we continue to push the boundaries of human spaceflight, the knowledge gained from space medicine research will be essential in ensuring the health, safety, and success of future astronauts. The quest to understand and overcome the medical challenges of spaceflight is not just about enabling exploration, it's about expanding the limits of human adaptation and resilience. As we develop solutions to keep humans healthy in the alien environment of space, we gain deeper insights into human physiology and psychology, potentially unlocking new approaches to healthcare on Earth. As we contemplate the medical challenges of long-duration spaceflight and the innovative solutions being developed to address them, we are reminded of the complexity of sustaining human life beyond our home planet. The field of space medicine intersects with numerous other areas of space technology and exploration, each presenting its own set of challenges and opportunities. One such area, which promises to revolutionize our capabilities in space and on Earth, is the rapidly advancing field of quantum computing. The potential applications of quantum computers in space exploration, from complex mission planning to data analysis, open up new frontiers in our quest to understand and navigate the cosmos. Quantum computing represents a revolutionary paradigm in information processing that holds immense potential for advancing space exploration. By harnessing the principles of quantum mechanics, these advanced computers promise to solve complex problems far beyond the capabilities of classical computers, while opening new frontiers in our understanding of the universe and our ability to navigate its vast expanses. The integration of quantum computing into space exploration is poised to transform various aspects of space science, from mission planning and data analysis to communication and navigation. At its core, quantum computing leverages the unique properties of quantum systems, such as superposition and entanglement, to perform computations. Unlike classical bits, which can be either 0 or 1, quantum bits, qubits, can exist in multiple states simultaneously, a phenomenon known as superposition. This property allows quantum computers to process vast amounts of information in parallel, potentially solving certain problems exponentially faster than classical computers. Entanglement, another key quantum phenomenon, enables qubits to be correlated in ways that have no classical counterpart, further enhancing the computational power of quantum systems. The potential applications of quantum computing in space exploration are vast and varied. One of the most promising areas is in the simulation of quantum systems, such as the behavior of atoms and molecules under extreme conditions. These simulations are crucial for understanding the physics of stellar interiors, planetary atmospheres, and the formation of complex molecules in space. Classical computers struggle with these simulations due to the exponential growth in complexity as the number of particles increases. Quantum computers, however, can naturally represent quantum systems, making them ideally suited for these types of simulations. Another significant application is in optimization problems, which are ubiquitous in space mission planning. Designing optimal trajectories for spacecraft, minimizing fuel consumption, and maximizing scientific return from limited resources are all complex optimization problems that could benefit from quantum algorithms. For example, the Quantum Approximate Optimization Algorithm, QAOA, has shown promise in solving combinatorial optimization problems more efficiently than classical algorithms. Applied to space exploration, this could lead to more efficient mission designs, reduced costs, and increased scientific output. The analysis of the vast amounts of data generated by space missions presents another challenge well suited to quantum computing. As space telescopes and probes collect increasingly detailed observations, the task of processing and extracting meaningful information from this data becomes more daunting. Quantum machine learning algorithms, which leverage quantum effects to enhance learning capabilities, could revolutionize how we analyze astronomical data. These algorithms could potentially identify patterns and anomalies in data that might be missed by classical methods, leading to new discoveries and insights into the nature of the universe. Quantum computing also holds promise for improving space communication and navigation. Quantum error correction techniques could enhance the reliability of communication in the presence of noise and interference, a significant challenge in deep space missions. Furthermore, Quantum sensors based on principles such as atom interferometry offer the potential for ultra-precise measurements of gravity, time, and position. These sensors could dramatically improve navigation in space, enabling more accurate positioning and timing for spacecraft and potentially supporting future technologies like quantum positioning systems for interplanetary travel. The development of quantum computers for space applications faces several unique challenges. The extreme environment of space, including vacuum, radiation, and temperature fluctuations, poses significant hurdles for maintaining the delicate quantum states necessary for computation. However, these challenges also present opportunities. The cold temperatures of space could actually be beneficial for certain quantum computing architectures that require cryogenic cooling. Research is ongoing into developing quantum computers that can operate reliably in the space environment, with potential designs ranging from superconducting circuits to trapped ions. Several space agencies and private companies are actively pursuing quantum computing applications for space exploration. NASA's Quantum Artificial Intelligence Laboratory, QAIL, in collaboration with Google and the university's Space Research Association, has been exploring quantum algorithms for optimization and machine learning problems relevant to space missions. The European Space Agency, ESA, has initiated programs to investigate quantum technologies for space applications, including a proposed quantum computer in space. These efforts highlight the growing recognition of quantum computing's potential to transform space exploration. One of the most exciting prospects for quantum computing in space exploration is its potential to enable breakthrough discoveries in fundamental physics. Quantum computers could be used to test theories of quantum gravity, explore the nature of dark matter and dark energy, and probe the limits of our current understanding of physics. For example, simulations of black hole dynamics or the early universe could provide new insights into the fundamental nature of space and time. The integration of quantum computing with other emerging technologies in space exploration could lead to synergistic advances. For instance, combining quantum computing with artificial intelligence could result in highly sophisticated autonomous systems capable of making complex decisions in real time during space missions. This could be particularly valuable for missions to distant planets or moons, where the time delay in communication with Earth necessitates greater onboard decision-making capabilities. As quantum computing technology advances, its impact on space exploration is likely to grow exponentially. Future quantum computers may enable the design of new materials for spacecraft and habitats, optimize life support systems for long-duration missions, and solve complex astrodynamical problems for interstellar travel. The ability to process and analyze vast amounts of data in real time could transform our approach to searching for extraterrestrial life, potentially allowing us to sift through the cosmic haystack with unprecedented efficiency. However, the development of quantum computing for space applications is not without challenges. The current generation of quantum computers is still in its infancy, with limited qubit counts and high error rates. Scaling up these systems while maintaining quantum coherence remains a significant technical hurdle. Additionally, developing quantum algorithms that offer practical advantages over classical methods for specific space-related problems is an ongoing area of research. The ethical implications of advanced quantum computing capabilities in space exploration also warrant consideration. As these technologies become more powerful, questions arise about their potential dual-use nature and the need for international cooperation and regulation in their development and deployment in space. In conclusion, quantum computing stands poised to revolutionize space exploration, offering unprecedented computational power to tackle some of the most challenging problems in space science and technology. From optimizing mission planning to enabling new discoveries in fundamental physics, the potential applications are vast and transformative. As research in this field progresses, we can anticipate a new era of space exploration, where the boundaries of our knowledge and capabilities are pushed further than ever before. The convergence of quantum computing and space exploration exemplifies the interdisciplinary nature of modern scientific endeavors. As we continue to push the frontiers of both quantum technology and space science, we are reminded of the intricate connections between the infinitesimally small world of quantum mechanics and the vast expanses of the cosmos. This intersection of the quantum and the cosmic leads us to consider other mysterious aspects of our universe, such as the nature of dark matter and its profound influence on the structure and evolution of the cosmos. In the vast expanse of our solar system, beyond the familiar terrestrial planets, lie worlds of unexpected diversity and potential. Among these, the oceanic moons orbiting the gas giants Jupiter and Saturn have emerged as some of the most intriguing targets for scientific exploration. These celestial bodies, including Europa, Enceladus, and Titan, harbor vast subsurface oceans beneath their icy crusts, presenting tantalizing possibilities for extraterrestrial life and offering unique insights into planetary formation and evolution. The concept of oceanic moons challenges our traditional understanding of where liquid water and potentially life might exist in the solar system. These moons, despite their great distance from the sun and frigid surface temperatures, maintain liquid water oceans due to a combination of internal heat generation and tidal forces exerted by their parent planets. This phenomenon expands the definition of the habitable zone, traditionally thought to be limited to a narrow band around stars where liquid water can exist on a planet's surface. Europa, one of Jupiter's Galilean moons, stands as a prime example of these ocean worlds. With a diameter of 3,100 kilometers, Europa is slightly smaller than Earth's moon, but harbors an ocean estimated to contain twice as much water as all of Earth's oceans combined. This vast body of water lies beneath an icy crust that may be only a few kilometers thick in some places. The energy required to maintain this liquid ocean comes primarily from tidal heating, caused by the gravitational pull of Jupiter and the other Galilean moons, as Europa orbits the gas giant. The surface of Europa, one of the smoothest in the solar system, is crisscrossed by a complex network of linear features, often referred to as chaos terrain. These features are thought to be evidence of the dynamic processes occurring in the ocean below, possibly including the cycling of materials between the surface and the subsurface. Recent observations by the Hubble Space Telescope have detected potential water vapor plumes erupting from Europa's surface, further supporting the idea of an active subsurface ocean and providing a potential means to sample its composition without the need to drill through the icy crust. Enceladus, a small moon of Saturn with a diameter of only 500 kilometers, has become another focal point in the search for extraterrestrial life. The Cassini mission, which studied the Saturn system from 2004 to 2017, made the groundbreaking discovery of geysers erupting from Enceladus's south polar region. These plumes, composed primarily of water vapor and ice particles, also contain organic compounds and other materials that suggest hydrothermal activity on the ocean floor. The presence of these compounds, including methane and hydrogen, has led scientists to speculate about the possibility of methanogenic life forms existing in Enceladus's ocean. The mechanisms maintaining liquid oceans on these moons involve complex interplays of gravitational forces, internal heat generation, and geological processes. In the case of Enceladus, tidal flexing caused by its eccentric orbit around Saturn is thought to generate enough heat through friction to maintain its subsurface ocean and drive the observed geologic activity. This process creates a potentially habitable environment that has persisted for millions or even billions of years. Titan, Saturn's largest moon and the only moon in the solar system with a substantial atmosphere, presents a unique case among oceanic worlds. While its surface is too cold for liquid water, Titan possesses seas and lakes of liquid hydrocarbons, primarily methane and ethane. Beneath its icy crust, however, lies a global ocean of water and ammonia. This complex system of surface and subsurface liquids makes Titan a compelling target for studying prebiotic chemistry and potential non-water-based life forms. The exploration of these oceanic moons presents significant technological challenges. The extreme cold, intense radiation environments around Jupiter and Saturn, and the need to penetrate thick ice crusts to access subsurface oceans all require innovative solutions. NASA's upcoming Europa Clipper mission, set to launch in the 2020s, will conduct detailed reconnaissance of Europa using a suite of instruments to study its composition, geology, and potential habitability. Similarly, the proposed Dragonfly mission to Titan aims to explore its unique surface environment using a rotorcraft drone. Detecting and studying potential life forms in these alien oceans is a complex endeavor. Scientists are developing techniques to identify biosignatures, chemical or physical signs of past or present life, that could be detected by future missions. These might include certain organic molecules, isotopic ratios, or patterns of chemical disequilibrium that are difficult to explain through abiotic processes alone. The potential for false positives, where non-biological processes mimic life signatures, necessitates a cautious and multifaceted approach to life detection. The study of oceanic moons has profound implications for our understanding of planetary habitability and the potential prevalence of life in the universe. If life is found to exist in these subsurface oceans, it would suggest that life can adapt to a much wider range of environments than previously thought, significantly expanding the number of potentially habitable worlds in our galaxy and beyond. Furthermore, these moons serve as natural laboratories for studying the conditions that may have existed on early Earth or on exoplanets orbiting other stars. The exploration of these worlds also drives technological innovation, developing systems capable of operating in extreme environments, such as autonomous submersibles that could explore subsurface oceans, has applications beyond space exploration. These technologies could be used to study Earth's deep oceans, polar regions, or other extreme environments. As our understanding of oceanic moons grows, new questions and areas for investigation continually emerge. The potential for material exchange between the surface and subsurface, the role of hydrothermal systems in sustaining potential ecosystems, and the long-term evolution of these ocean worlds are all active areas of research. Future missions may include landers or even submersibles designed to directly sample and analyze the composition of these alien oceans. The mystery of oceanic moons represents one of the most exciting frontiers in planetary science and astrobiology. These worlds challenge our perceptions of where life might exist and offer tantalizing possibilities for discoveries that could reshape our understanding of life's potential in the cosmos. As we continue to explore these distant moons, we edge closer to answering one of humanity's most profound questions. Are we alone in the universe? As we contemplate the vast oceans hidden beneath the icy surfaces of these distant moons, we are reminded of the incredible diversity of worlds within our own solar system. The potential for life in these alien environments sparks our imagination and drives our exploration efforts. Yet, as we look outward to these mysterious moons, we are also compelled to consider the grandest structures we can imagine, not just in our solar system, but on a cosmic scale. This brings us to ponder the concept of megastructures in space, hypothetical constructions of staggering proportions that push the boundaries of engineering and challenge our understanding of what advanced civilizations might be capable of achieving. As humanity's technological capabilities advance and our ambitions in space exploration grow, the concept of megastructures in space has captured the imagination of scientists, engineers, and visionaries alike. These colossal constructions, existing primarily in the realm of theoretical physics and speculative engineering, represent the pinnacle of what advanced civilizations might achieve in their quest to harness the resources of their star systems and expand beyond their home planets. From Dyson spheres that encapsulate entire stars to massive space habitats that could house millions, megastructures challenge our understanding of engineering limits and offer tantalizing glimpses into potential futures of space colonization and energy production on an astronomical scale. The concept of space megastructures gained prominence in scientific discourse with the publication of Freeman Dyson's 1960 paper, Search for Artificial Stellar Sources of Infrared Radiation. Dyson proposed that advanced civilizations might construct a shell or swarm of satellites around their star to capture most or all of its energy output. This concept, now known as a Dyson sphere, has become a cornerstone of discussions about megastructures and potential signatures of extraterrestrial intelligence. A full Dyson sphere, enclosing an entire star, would be an engineering feat of almost unimaginable proportions. With a radius equal to that of Earth's orbit, 1 astronomical unit or AU, such a structure would have a surface area of approximately 550 million times that of Earth. The materials required for such a construction would likely exceed the total mass of all planets in a typical solar system, necessitating the mining of entire planets or the harvesting of material from the star itself. While a solid shell is often depicted in popular culture, more practical variations include the Dyson swarm, consisting of millions of independent solar collectors orbiting the star, or a Dyson bubble, where the collectors are statites, objects using the star's radiation pressure to maintain their position. The primary purpose of a Dyson sphere or its variants would be to capture and utilize the entirety of a star's energy output. For context, the total energy output of the Sun is approximately 3.828 x 10 toward 26 watts, vastly exceeding the current energy consumption of human civilization by many orders of magnitude. A civilization capable of harnessing this level of energy would be classified as a Type 2 on the Kardashev scale, a hypothetical measure of a civilization's level of technological advancement based on its energy utilization. Another class of megastructures that has garnered significant attention is large-scale space habitats. Concepts like the O'Neill cylinder, proposed by physicist Gerard K. O'Neill in the 1970s, envision massive rotating structures that could provide Earth-like living conditions for millions of inhabitants. A typical O'Neill cylinder might be 5 miles, 8 kilometers in diameter and 20 miles, 32 kilometers long, rotating to produce artificial gravity through centrifugal force. These habitats would need to address numerous engineering challenges, including radiation shielding, atmosphere containment, and the psychological effects of enclosed living spaces. The construction of megastructures in space would require overcoming numerous technological hurdles. The development of advanced materials with unprecedented strength-to-weight ratios would be crucial. Current materials like carbon nanotubes and graphene show promise, but scaling their production to the levels required for megastructures remains a significant challenge. Additionally, the logistics of assembling structures on such a massive scale in the vacuum of space would necessitate breakthroughs in robotics, automation, and in-space manufacturing. Energy management on the scale of megastructures presents another set of challenges. While Dyson spheres are conceptualized as energy-gathering structures, the distribution and utilization of that energy across vast distances would require technologies far beyond our current capabilities. Concepts like wireless power transmission using microwave beams, or even more exotic ideas involving the manipulation of space-time to transfer energy, might need to be developed. The search for extraterrestrial intelligence, SETI, has incorporated the concept of megastructures into its observational strategies. The idea that advanced civilizations might construct Dyson spheres or similar structures has led to searches for their potential signatures. These searches focus on detecting infrared excess from stars that might indicate the presence of a large, warm structure surrounding them. The controversy surrounding KIC 84628552, also known as Tabby's star, which showed unusual dimming patterns, briefly reignited interest in the possibility of detecting alien megastructures, though natural explanations for the star's behavior have since been favored. While full-scale megastructures remain firmly in the realm of speculation for now, smaller-scale projects that could be seen as precursors to such structures are being seriously considered. Space-based solar power stations, while much smaller than a Dyson swarm, operate on similar principles of capturing solar energy in space and beaming it to Earth. NASA and other space agencies have conducted studies on the feasibility of such systems, which could provide clean, continuous energy to Earth. The implications of megastructures for the future of humanity and our understanding of the universe are profound. The ability to construct and inhabit large-scale space habitats could be key to becoming a truly spacefaring civilization, allowing for the colonization of star systems beyond our own. The energy-gathering potential of Dyson-like structures could solve energy crises and fuel further technological advancements. Moreover, the process of developing the technologies necessary for megastructures would likely yield numerous benefits applicable to other areas of science and engineering. The concept of megastructures also raises philosophical and ethical questions about the long-term goals and impacts of advanced civilizations. The transformation of entire star systems to suit the needs of a species represents a level of cosmic engineering that would fundamentally alter the natural state of the universe. This leads to considerations about the responsibilities that come with such capabilities and the potential impacts on any existing ecosystems or other civilizations that might exist. As we continue to expand our presence in space and push the boundaries of our technological capabilities, the study of megastructures serves as both an inspiration and a roadmap for future developments. While the full realization of such structures may be centuries or millennia away, the concepts drive innovation in fields ranging from materials science to energy production and space habitation. The exploration of megastructure concepts challenges us to think on cosmic scales and consider the ultimate potential of technological civilizations. As we grapple with the engineering, physical, and ethical implications of such grandiose constructions, we are pushed to expand our understanding of the universe and our place within it. The journey towards realizing even small-scale precursors to these megastructures will undoubtedly yield discoveries and technologies that will benefit humanity in myriad ways, both on Earth and in our ongoing exploration of the cosmos. As we contemplate the awe-inspiring scale and implications of cosmic megastructures, we are reminded of the vast potential that lies ahead in our journey of space exploration and technological advancement. These concepts, while currently beyond our reach, serve as beacons guiding our scientific and engineering endeavors toward ever more ambitious goals. Yet, as we dream of reshaping star systems and harnessing the power of suns, we must also turn our attention back to the more immediate challenges and opportunities that space exploration presents. One such frontier, bridging our current capabilities with our future aspirations, is the rapidly evolving field of space tourism, which promises to bring the experience of spaceflight to a broader audience and potentially reshape our relationship with space exploration.